Hello, and welcome to this comprehensive preparation course for the IBM C1000-142 Cloud Advocate V2 certification. This is an unofficial, independently produced course and study guide. It is not affiliated with, endorsed by, or connected to IBM in any way. All trademarks belong to their respective owners. In this introductory module, we will outline the core objectives of the certification and establish the foundational knowledge required to pass the exam. You will gain a clear understanding of cloud computing paradigms, architectural principles, security frameworks, and the billing methodologies that underpin the IBM Cloud ecosystem. This course is designed to be your primary guide, transforming the official exam blueprint into a structured, manageable learning path. We will cover the technical details of infrastructure, storage, and networking while ensuring you feel comfortable navigating the IBM Cloud Console. By the time we reach the end of our journey, you will possess not only the theoretical knowledge to pass the test, but also a practical understanding of how these services function in modern environments. We will also dedicate time to discussing effective study strategies and the importance of practice exams and identifying your knowledge gaps. You will learn how to create your own IBM Cloud account to facilitate hands-on learning, which is essential for grounding abstract concepts in reality. My goal is to ensure that you are fully prepared for the format, time limits, and specific question types you will encounter on the day of your assessment. I look forward to guiding you through these topics and helping you achieve your certification goals. See you in the next lecture. Hello, and welcome back. In this chapter, we will examine the defining characteristics of cloud computing that distinguish it from traditional IT infrastructure. To understand modern cloud computing, we must start with the 5 essential characteristics defined by the National Institute of Standards and Technology. The first of these is on-demand self-service, which allows consumers to provision computing capabilities like server time or network storage automatically without human interaction with the service provider. This eliminates the lengthy procurement cycles that were once standard in enterprise IT environments. Closely related to this is broad network access, ensuring that these capabilities are available over the network and accessed through standard mechanisms that promote use by heterogeneous thin or thick client platforms. Whether you're using a mobile phone, a laptop, or a desktop, the interface remains consistent and accessible. This universality is what transforms isolated workloads into interconnected, accessible services. Without these two pillars, the promise of the cloud would remain stuck in the architectural constraints of the past. It shifts the burden of availability from the local administrator to the service provider's infrastructure. The third characteristic is resource pooling, where the provider's computing resources are aggregated to serve multiple consumers using a multi-tenant model. Physical and virtual resources are dynamically assigned and reassigned according to consumer demand, often without the consumer knowing the exact location of the hardware. This abstraction is made possible through virtualization and containerization technologies that create logical separation between tenants sharing the same physical pool. Rapid elasticity is the fourth pillar, providing the ability to scale resources outward and inward, commensurate with demand. From an observer's perspective, these capabilities often appear to be infinite and can be purchased in any quantity at any time. This stands in stark contrast to static capacity planning, where you had to provision for peak load regardless of actual utilization. The final characteristic is measured service, which ensures that cloud systems automatically control and optimize resource use by leveraging a metering capability. When we analyze the financial implications of these characteristics, we inevitably arrive at the shift from capital expenditure, or CapEx, to operational expenditure, or OpEx. In a legacy environment, organizations treat IT as a capital asset, requiring significant upfront investment in hardware and data center space that depreciates over time. In the cloud, this becomes an operational expense, treated as a pay-as-you-go consumption model that aligns directly with business value. This transition introduces financial flexibility that allows organizations to experiment with new ideas without the heavy burden of sunk costs. However, this flexibility also necessitates a shift in how we approach the shared responsibility model. Cloud providers are responsible for the infrastructure, which encompasses the physical hardware, networking, and the virtualization layer. Meanwhile, the consumer remains responsible for data, application configuration, and identity management. which is a distinction that often requires a paradigm shift in how security teams operate. The evolution of these characteristics is grounded in historical shifts, progressing from the mainframe era through grid computing toward our current cloud architectures. Mainframes focused on central control and high availability, but lacked the agility required by modern web-scale enterprises. Grid computing attempted to decentralize resources, but remained complex to standardize across disparate environments. Cloud computing synthesizes these histories by applying the abstraction of the hypervisor to create scalable, elastic, and measurable environments. We no longer treat servers as snowflake configurations, but as ephemeral components that can be replaced or scaled automatically. These foundational technologies enable modern enterprise workloads to prioritize resilience and continuous innovation over maintenance of hardware. As you prepare for the examination, keep in mind how these 5 characteristics interact to produce the agility required for digital transformation. I look forward to discussing how these concepts translate into service models in the next video. Hello and welcome. In this session, we will explore the infrastructure as a service model and how it shifts the responsibility of hardware management to the cloud provider. Infrastructure as a service, or IaaS, represents the most fundamental layer of cloud computing models. At its core, it provides virtualized computing resources delivered over the internet, effectively abstracting physical hardware away from the end consumer. Instead of purchasing, racking, and cooling physical servers in an on-premises data center, an organization consumes processing power, storage, and networking components as a service. This model allows for the deployment and execution of arbitrary software, including full operating systems and complex application stacks. You maintain granular control over the software environment, while the provider assumes the burden of maintaining the underlying physical infrastructure such as power, cooling, and hardware maintenance. This shift significantly reduces the data center footprint and capital expenditure, enabling businesses to scale resources up or down based on immediate demand. When we transition to IaaS, we are essentially interacting with virtualization layers rather than bare metal hardware. The provider utilizes hypervisors to partition physical hosts into multiple virtual machines, each capable of running its own guest operating system. From your perspective, you manage the virtual machine lifecycle, which includes installing patches, configuring network interfaces, and attaching block or file storage. You define the virtual private cloud boundaries, establishing subnets, and configuring security groups to act as virtual firewalls. Despite this high level of control, you remain responsible for securing the operating system, the runtime environments, and the data stored within these instances. The provider, conversely, ensures that the hypervisor remains updated. The underlying network fabric is operational, and the physical hosts possess sufficient capacity to support your workloads. The benefits of adopting an IaaS model are particularly evident in environments that require rapid elasticity and cost efficiency. Consider test and development scenarios, where developers need to spin up identical production-like environments in minutes and tear them down once testing is complete. Traditional hardware procurement cycles simply cannot match this velocity, whereas IaaS allows for programmatic provisioning through APIs or command line interfaces. Furthermore, website hosting, high-performance computing, and specialized storage for backup and recovery are primary use cases where IaaS excels. By offloading the hardware lifecycle management to the provider, organizations can redirect their focus toward optimizing their applications rather than worrying about hard drive failures or hardware degradation. This increases operational agility and ensures that compute utility is tightly aligned with actual business consumption. However, working within an IaaS framework requires an understanding of the relationship between virtualized components and their underlying constraints. In an on-premises deployment, you have total visibility and control over network latency and bandwidth at the physical switch level. In a cloud environment, you must account for network abstraction layers that govern communication between virtual machine instances and the broader internet. When you configure a virtual private cloud, you are defining a software-defined networking ecosystem where subnets, routing tables, and gateway services determine performance and connectivity. Monitoring these metrics is essential because poor configuration of security groups or improper placement of instances across availability zones can inadvertently create bottlenecks. Mastery of this layer requires you to treat infrastructure as code, ensuring that your provisioning patterns remain consistent, repeatable, and secure. I look forward to seeing you in the next session. Welcome back. In this lesson, we explore the platform as a service model, focusing on how it provides managed environments to streamline application development and deployment. Platform as a service, or PaaS, represents a shift in focus from managing servers to delivering business value through code. When you adopt a PaaS model, you are essentially offloading the maintenance of the operating system, hardware, network configurations, and storage abstractions to the cloud provider. This is not just a convenience, but a strategic decision to enable developers to concentrate exclusively on the application lifecycle. By removing the need to patch kernels or manage hardware lifecycle events, teams can significantly accelerate their time to market for new features. The provider manages the underlying runtime environment, which allows for a more consistent experience across development, staging, and production environments. You gain access to pre-built components like middleware and database systems that are ready for immediate use. This architectural choice inherently shifts the shared responsibility boundary, placing more operational burden on the vendor while granting your team more agility. The core value proposition of PaaS lies in its ability to support modern architectural styles like microservices and event-driven computing. Because the platform provides the infrastructure as a consumable service, it naturally integrates with continuous integration and continuous delivery pipelines. You will often find automated scaling and self-healing features baked into the very fabric of these environments. If an instance underperforms or becomes unreachable, the platform orchestration layer detects this failure and replaces it without direct manual intervention. This is a critical advantage when scaling mobile app backends or managing Internet of Things device streams. Furthermore, security and compliance are handled at the platform level, which can simplify your adherence to industry standards. As the complexity of modern applications increases, having these features managed by the cloud provider ensures that your focus remains on logic and business outcomes rather than infrastructure plumbing. We should also consider how PaaS contrasts with infrastructure as a service to better understand why you would choose one over the other. With infrastructure as a service, you retain full control over the operating system, which is sometimes necessary for legacy applications or specific performance requirements. However, this control entails administrative overhead that often distracts from development goals. PaaS optimizes for developer productivity by abstracting those complexities away. Whether you are using container orchestration platforms or serverless computing models, the goal remains the same: reducing the glue code required to connect services. By using built-in development tools and business intelligence services, you effectively increase the velocity of your engineering teams. Collaboration becomes seamless because the entire team operates against a standardized set of platform interfaces and managed services provided by the cloud vendor. See you in the next lecture. Welcome back to our exploration of cloud delivery models, where we now turn our attention to software as a service. This lesson covers the architecture and operational realities of SaaS, providing the foundational knowledge you need to master this exam topic. Software as a service, or SaaS, represents a fundamental departure from the legacy model of software acquisition, where an organization would purchase a perpetual license, install the binaries on local hardware, and manually manage the lifecycle of that application. In a SaaS paradigm, the application itself is hosted and maintained by the cloud provider, and users simply access the functionality via a web browser or a thin client. This shift moves the burden of infrastructure, security, and maintenance from the customer to the provider, fundamentally changing the economics of software consumption. By moving to a subscription-based model, businesses shift their expenditure from significant upfront capital investments to predictable operating expenses. This agility allows organizations to adopt new technologies without the traditional long lead times associated with procurement and installation. We are essentially trading local control for standardized service delivery. This model acts as the highest layer in the cloud computing stack, abstracting away virtually all complexity regarding the underlying compute, storage, and networking layers. The primary advantages of this approach include automatic updates and seamless patch management, which ensure that every user is always interacting with the latest version of the platform. Because the application is hosted centrally, global accessibility is achieved inherently, allowing users to connect from any location with an internet connection, regardless of the physical device being used. This device independence drastically simplifies support operations for IT departments, as they no longer need to worry about hardware compatibility issues or local OS-level patches. Furthermore, the pricing structure is typically predictable, allowing organizations to forecast costs based on per-user or per-feature metrics rather than unpredictable maintenance windows. Common enterprise examples span across critical business functions, including customer relationship management systems, enterprise resource planning, and human resources information systems. Collaborative productivity suites and unified communication tools are also classic manifestations of SaaS, enabling real-time collaboration without the friction of deploying local instances. This global, always-on availability is the cornerstone of modern digital transformation in the enterprise. Despite these clear benefits, we must acknowledge the inherent constraints and architectural challenges that come with multi-tenant designs. Multi-tenancy involves a single instance of software serving multiple customers, which requires sophisticated data segregation techniques to ensure that one customer cannot see or impact the data of another. While providers utilize robust logic to separate data storage and processing, concerns regarding data residency and sovereign compliance can persist in highly regulated industries. Integration with legacy on-premises systems remains one of the largest hurdles, as SaaS applications are generally built for public API interaction rather than direct database connectivity via private lines. Furthermore, customers must be acutely aware of vendor lock-in risks, where migrating data and replatforming processes becomes prohibitively difficult if a vendor changes their terms or service viability. Identity management is also critical here, as systems must integrate seamlessly with enterprise-grade identity federation and single sign-on protocols to ensure authorized access across a distributed workforce. To maintain the operational integrity of these services, providers rely heavily on detailed service-level agreements, which mandate platform availability and define the service expectations for the business. These agreements are not merely legal documents. They formalize the relationship between the technical uptime of the application and the business continuity of the customer. In a SaaS environment, the provider assumes responsibility for the underlying server infrastructure, the application runtime, and the data layer security, but the customer remains responsible for managing their internal access policies. Effective usage of SaaS requires that companies audit their identity providers, role assignments, and permission structures frequently to mitigate the risk of unauthorized access. While we sacrifice the ability to perform deep, engine-level customizations, such as modifying the core source code of an ERP system, we gain the immense benefit of shared innovation across the provider's entire user base. Every enhancement released by the provider is immediately available to the consumer, reinforcing the cyclical nature of cloud service evolution. See you in the next lecture. Hello, and welcome back. In this chapter, we will explore the foundational differences between public and private cloud deployment models to help you master the core concepts of infrastructure architecture. Public cloud environments represent services offered by third-party providers, delivering computing resources over the public internet to any consumer willing to pay for them. These environments rely on multi-tenant architecture, where the underlying physical hardware is shared among various customers to achieve high utilization and cost efficiency. When you opt for a public cloud, you are essentially renting space in a massive, abstracted infrastructure pool, which benefits from economies of scale that few individual organizations could replicate on their own. This model is synonymous with a pay-as-you-go pricing paradigm, shifting the financial burden from large, upfront capital expenditures to predictable, ongoing operational expenses. Because the provider manages the hardware, networking, and maintenance, public clouds offer incredible agility and almost instantaneous scalability. However, this accessibility comes with the trade-off of shared infrastructure, which requires trusting the provider to enforce strict logical isolation between different tenants. Understanding this balance is central to the IBM Cloud Advocate perspective, as most cloud-native applications are designed to thrive in these shared, elastic environments where horizontal scaling is the default expectation for managing variable workloads. Conversely, private cloud infrastructures are dedicated exclusively to a single organization, providing a more isolated and controlled computing environment. These deployments can be hosted on premises within a company's own data center or managed by a third-party service provider in a hosted private model. The primary driver for choosing a private cloud is often the requirement for enhanced security, data privacy, and strict adherence to regulatory compliance standards, which are common in industries like finance, healthcare, and government. Since the infrastructure is not shared with other tenants, representing a single-tenant environment, the organization maintains full control over the configuration of the hardware, the software stack, and the security protocols. This results in higher upfront capital expenditure because the organization must procure or lease the dedicated physical assets regardless of actual utilization rates. While this removes the noisy neighbor effect associated with multi-tenancy, it also introduces higher management overhead as the responsibility for maintenance, updates, and orchestration falls on the internal IT staff rather than the cloud provider. The decision to use a private cloud often hinges on whether the organization's specific workload requirements mandate the degree of customization and total physical isolation that a public cloud simply cannot provide by design. When we compare these models, the distinction between multi-tenant and single-tenant architectures helps explain the trade-offs regarding cost, scalability, and control. Public clouds offer superior scalability limits because they tap into a global pool of resources, whereas private clouds are limited by the physical capacity of the dedicated hardware installed within the defined environment. While public clouds allow for rapid deployment and lower entry costs through operational expenditure, private clouds provide the granular customization and regulatory compliance comfort necessitated by mission-critical or sensitive data. It is important to note that modern cloud architecture often blurs these lines through the use of virtual networks, which represent logical isolated partitions within public platforms. These virtual networks give organizations the ability to mimic the private networking capabilities and security boundaries of an on-premises setup, while still benefiting from the public cloud's underlying compute and storage elasticity. By using these logical constructs, architects can build environments that appear private to the application, having their own subnets, routing tables, and firewalls, while physically existing within the broader, multi-tenant public infrastructure. This synthesis allows organizations to maintain control over their data traffic, ensuring that communication between their workloads remains protected from external exposure while still utilizing the agile, scalable services of a global provider. I will see you in the next lesson. Welcome back. In this lesson, we explore how hybrid and multi-cloud models allow organizations to combine disparate infrastructure environments into a cohesive, functional architecture. When we talk about hybrid cloud environments, we are essentially looking at the intersection of private data centers and public cloud service providers. This architecture is rarely a purely aesthetic choice. Rather, it is a pragmatic response to the reality that moving every single workload to a public cloud is often impossible or strategically unwise. By maintaining sensitive legacy data on-premises while leveraging the elastic computational power of the public cloud, a business gains significant agility. You can think of this as a form of architectural balancing, where you scale your web-tier workloads to the cloud during peak demand, commonly referred to as cloud bursting, while keeping your core regulatory-sensitive data behind your own firewall. This hybrid approach allows for a graduated migration, acknowledging that technical debt and regulatory requirements often prevent a wholesale shift to a public environment. The fundamental goal is to treat these disparate zones as a single, connected ecosystem. Achieving this requires robust connectivity, often through dedicated high-speed links, to ensure that the latency between the local data center and the cloud provider is kept to a minimum. Multi-cloud strategies represent a different, yet often overlapping, layer of complexity where an organization intentionally distributes its services across multiple cloud vendors. The primary driver here is typically the avoidance of vendor lock-in, which is the concern that your proprietary code will become so tightly coupled to a single provider's API that moving away becomes prohibitively expensive. By adopting a multi-cloud approach, you maintain the flexibility to move workloads if a provider changes their pricing structure or if their feature set no longer aligns with your long-term technical goals. You are also essentially hedging your bets regarding redundancy, ensuring that a regional outage at one provider does not result in a total service blackout for your customers. Furthermore, this strategy allows development teams to leverage best-of-breed services, such as choosing one provider for their superior natural language processing tools and another for their high-performance block storage. Managing these heterogeneous environments, however, comes with a significant overhead in terms of cognitive load and operational complexity. You no longer have the luxury of learning a single set of management tools or monitoring dashboards. Integration challenges are the inevitable trade-off when you choose to fragment your infrastructure across multiple providers or combine public and private tiers. Data portability often serves as the most difficult hurdle, as different cloud providers use proprietary formats, storage APIs, and networking models that do not natively interoperate. When you need to relocate a large dataset or a virtual machine image, you often find yourself dealing with extensive data egress costs and time-consuming synchronization tasks. Workload migration strategies must therefore be carefully planned, emphasizing the use of containerization, particularly with technologies like Kubernetes, to decouple the application from the underlying infrastructure. Interoperability standards, including those supported by the Cloud Native Computing Foundation, provide a necessary baseline for ensuring that your software can move consistently between environments. Security remains another critical, often overlooked dimension in these complex architectures. When your environment spans across boundaries, you face the significant challenge of normalizing security policies and ensuring that identity and access management settings are consistently applied across all endpoints. Unified management is the only viable way to maintain visibility in such a distributed, heterogeneous environment. You need a centralized monitoring and management plane that can aggregate logs, metrics, and security alerts from your private data centers, as well as every public cloud provider in your architecture. Without this centralized view, you risk operating in silos where performance bottlenecks or misconfigured security groups in one location go unnoticed until they become a critical failure. Many organizations address this by adopting open source technologies or vendor-neutral management software that provides a consistent lens. You should consider how identity propagation functions across these borders, ideally using a centralized identity provider so that an engineer has a single set of credentials to access resources regardless of their location. Effective hybrid and multi-cloud strategies rely on being able to abstract the underlying complexity, providing your development teams with a consistent experience regardless of whether their service is hosted in a virtual server on premises or a container cluster in the public cloud. Success here is not about building the most complicated architecture, but about building the most resilient management capability. I will see you in the next lecture. Welcome back. In this chapter, we explore the physical foundation of the IBM Cloud platform, focusing on its extensive global footprint and regional architecture. When we talk about global presence in the context of cloud infrastructure, we are essentially looking at the physical scaffolding that supports software execution. IBM Cloud has strategically positioned its data centers across the globe to transform the abstract concept of a public cloud into a concrete, low-latency reality for enterprise customers. This footprint is not merely a collection of scattered server rooms, but a tightly integrated network designed for high availability and performance. By placing compute and storage resources closer to the end user, the platform reduces transit time and ensures that applications remain responsive even under heavy demand. For an architect, understanding this distribution is the first step in designing solutions that comply with various data sovereignty laws. If you need to keep data within a specific jurisdiction to satisfy regulatory requirements, the ability to pin your services to a particular region or geography is not just a feature, it is a fundamental requirement. This physical proximity is what ultimately dictates the baseline performance and legal profile of your cloud-deployed workload. The infrastructure is built upon a tiered architecture that moves from broad geographies down to specific data centers, all stitched together by a highly redundant backbone. This private network is largely unmetered, meaning that traffic moving between IBM Cloud data centers across different continents does not suffer from the same latency or cost unpredictability found on the public internet. This high bandwidth interconnectivity is critical for complex, distributed applications that need to synchronize databases or replicate file storage in near real time. Because the network backbone is owned and managed by IBM, it offers a level of predictability and security that third-party routing cannot guarantee. When you deploy an application, you are leveraging this underlying mesh to ensure that your backend services can communicate securely and rapidly across global boundaries. This architecture facilitates seamless international deployments, allowing a single logical workload to be distributed across multiple regions while maintaining a unified operational view. Beyond simple connectivity, This global presence serves as the bedrock for your disaster recovery and high availability strategies. A robust architecture assumes that failures will occur, whether they are localized power outages or regional connectivity issues. By distributing your infrastructure across multiple zones and regions, you can design for fault tolerance, ensuring that if one site goes dark, your traffic is redirected or your application state is recovered elsewhere. This is closely integrated with content delivery network capabilities and edge caching, which push static assets to the periphery of the network to minimize the distance data must travel. Enterprise service level agreements often hinge on this ability to maintain uptime despite physical infrastructure failures. Architects who ignore the physical layout of their cloud provider often find themselves trapped by rigid designs when they need to scale internationally or meet strict regulatory audit standards. Master the geography of your provider, and you gain the leverage to build systems that are as resilient as they are scalable. In the next lecture, we will examine how these physical concepts translate into the specific administrative units you will interact with daily. See you in the next lecture. Hello, welcome back. In this lesson, we will examine the structure of IBM Cloud regions and the geographic implications for your architecture. To understand the IBM Cloud footprint, we must first define what a region represents in a cloud architecture. A region is a geographically distinct territory that serves as the foundation for your deployment. Within these boundaries, IBM hosts one or more availability zones, which are physically isolated data centers. These zones are connected by high bandwidth, low latency networking, ensuring that communication between them is fast enough to support distributed systems. The primary reason for this architectural choice is fault isolation. By design, a region is meant to contain potential failures, preventing a localized event from cascading across the entire global infrastructure. If a power grid issue or a network disruption occurs in a specific area, it should remain limited to that environment, thereby protecting the rest of your business workloads elsewhere. This localized high availability is the first line of defense for critical applications that cannot afford downtime. Choosing the right region is rarely just a technical decision based on proximity to your end users. While reducing physical distance often results in lower latency for your users, you must also weigh legal requirements and data residency laws. Many jurisdictions now mandate that customer data remain within national borders, which necessitates careful selection of your regional deployment. Furthermore, service availability and pricing can fluctuate between regions, meaning you must check if specific IBM Cloud services are supported in the area you intend to use. Some regions may offer specialized hardware or newer service features that are not yet rolled out globally. You should always consult the documentation for the specific location to confirm that your required service portfolio matches your business needs and your budget constraints. When looking at the internal structure of these regions, we encounter the difference between single-zone and multi-zone regions. A single-zone region carries a higher risk because your entire stack resides in one facility, making it vulnerable to any physical disaster occurring in that building. In contrast, a multi-zone region consists of several independent zones, which allows you to distribute your application components for true fault tolerance. By spreading resources across multiple zones, you ensure that if one zone experiences an outage, the other zones can continue processing traffic. This is a standard practice for production-grade, business-critical workloads that require high availability guarantees. Designing for this model is essential if you want to eliminate single points of failure within your cloud environment. IBM maintains a global distribution of these regions across North America, Europe, Asia-Pacific, and South America to meet the needs of international organizations. However, physical presence in a region is only one part of the equation when designing for system resilience. You need an effective cross-region communication strategy to handle scenarios where an entire region might face disruption. This often involves asynchronous data replication to maintain copies of your databases in a secondary region. Additionally, implementing global load balancing can direct traffic away from a failing region to a healthy one, facilitating disaster recovery. These topologies are not merely advanced options. They are core requirements for any architecture that demands continuity. By mastering these concepts, you gain the ability to build systems that remain operational even in the face of significant regional hardware or network failures. I look forward to our next session. Welcome. Let us look at how IBM Cloud organizes its physical infrastructure through availability zones. This chapter focuses on the architectural building blocks that provide resilience for your cloud applications. In the IBM Cloud ecosystem, a region is composed of multiple availability zones, which are isolated locations designed to operate independently. Each zone houses its own physical infrastructure, including dedicated power, cooling, and network hardware, effectively insulating it from failures in neighboring facilities. While these zones are physically separate to minimize the risk of concurrent outages, they are interconnected via high-bandwidth, low-latency networking links. This design is foundational for building highly available systems, as it allows architects to distribute components across independent failure domains. From an application perspective, this means you can survive a localized hardware malfunction or a utility outage by ensuring your service instances span across these defined zones. The physical separation is not just a logical abstraction. It represents a commitment to business continuity by preventing a single point of failure at the facility level. Achieving high availability requires a conscious architectural decision to deploy workloads across multiple zones within a single multi-zone region. When you spread your application components, such as compute instances or database nodes, across these zones, you reduce the blast radius of any maintenance event or unexpected facility shutdown. The strict low-latency constraints enforced between zones enable sophisticated patterns like synchronous data replication, which is essential for maintaining strict consistency in database clusters. Likewise, microservices that rely on high-frequency communication benefit from this proximity, as they avoid the performance penalties associated with long-distance network travel. You should view multi-zone deployment as your primary defense against regional platform instability. By treating each zone as a modular unit of infrastructure, you can design systems that fail over automatically without user intervention. Architecting for multi-zone resilience often involves the use of redundant load balancers that distribute incoming traffic across healthy zones. By placing your container orchestration clusters, such as those running on OpenShift, across these boundaries, you ensure that the control plane and worker nodes remain functional, even if one zone experiences a degradation. Automated failover mechanisms are then triggered by health checks, which redirect user requests to the remaining active zones while the affected infrastructure remains isolated. It is a common misconception that simply choosing a cloud provider grants you automatic high availability for all components. Instead, the shared responsibility model dictates that while IBM is responsible for the redundancy of the physical and network infrastructure, you as the user must explicitly configure your applications to leverage these capabilities. You must decide where your data resides and how your compute instances are distributed to satisfy your specific uptime requirements. When working with these deployments, it is important to understand that not every service is universally available or identical in every single zone from day one. Providers often follow a gradual rollout strategy for new features, where functionality may appear in primary zones before reaching others. Therefore, it is part of your operational duty to verify service presence and capability alignment within the specific zones you intend to target during the provisioning phase. This check ensures that you do not encounter unexpected limitations when deploying global services that require specific back-end support. Keeping your configuration scripts and infrastructure as code templates synchronized with the actual zone-specific capabilities is a hallmark of a mature cloud engineering practice. This granular attention to the location of your resources is what separates a fragile application from a resilient, production-grade system. See you in the next lecture. Welcome to the section on IBM Cloud Architecture Basics, where we will examine the structural foundations necessary for effective cloud resource management. We will specifically focus on resource groups as the primary logical containers for your platform assets. In the ecosystem of IBM Cloud, resource groups serve as the foundational mechanism for organizing your digital assets. Think of them not merely as folders, but as logical boundaries that allow you to group your platform as a service resources, application services, and their associated identity and access management policies. This architectural choice is significant because it provides a unified way to manage your cloud footprint across different geographic regions. When you assign resources to a group, you are effectively creating a management silo that simplifies how your team interacts with the underlying infrastructure. By transitioning to this model, you move away from fragmented management and toward a centralized paradigm where access control and billing management become consistent and predictable. One of the most compelling reasons to utilize resource groups is the ability to implement granular access management. Instead of applying permissions to individual services, which is tedious and error-prone, administrators can assign specific roles at the group level. This capability is particularly transformative for onboarding new developers to your project teams. By granting a user access to a specific resource group, they automatically inherit the correct permissions for all the services contained within that group. This approach drastically minimizes the risk of over-provisioning access and removes the manual friction typically associated with scaling development teams. You are essentially shifting the complexity of user permissions from the resource layer to the container layer, which is a much more maintainable pattern for long-term operations. It is vital to understand that the architecture of resource groups is not fluid in the way one might initially expect. Once an instance has been provisioned into a specific resource group, it cannot be migrated to another group at a later time. This limitation necessitates a disciplined approach to your initial cloud architecture planning and the establishment of rigid naming conventions. If you fail to design your group hierarchy correctly from the start, you will be forced to recreate resources to fix your organizational structure. Therefore, the upfront investment in designing your group topology pays dividends in the long run. I encourage you to view your resource groups as permanent infrastructure definitions rather than temporary categorization labels. Considering how to organize your deployments, the most effective strategies often mirror the reality of your software development lifecycle and organizational hierarchy. Many teams find success by grouping resources based on lifecycle stages such as development, testing, staging, and production. Other organizations prefer to group assets by business unit or specific project boundaries, which provides clear visibility into ownership and accountability. Regardless of the chosen methodology, the key is to remain consistent across your account. By doing so, you create a standard taxonomy that is easy for engineers to understand and easy for automated systems to parse. A well-organized account is far easier to audit and troubleshoot than one where resources are scattered without a discernible pattern. Beyond organizational efficiency, resource groups provide powerful integration points with IBM Cloud cost management tools. Because each group acts as a distinct bucket for resources, the platform can aggregate usage data with remarkable precision. This facilitates granular chargeback reporting, allowing finance teams to understand exactly how much a particular project or department is spending on cloud consumption. Furthermore, you can set budget alerts keyed to specific resource groups, enabling proactive cost control before overrun occurs. The ability to track spending at this level is a foundational requirement for any mature cloud strategy that prioritizes financial accountability and operational transparency. When the accounting department asks for a breakdown of your cloud bill, you will find that a thoughtful group structure makes that report almost instantaneous. Take care as you plan your resource hierarchy. I look forward to our next session together. Welcome to this new chapter where we will explore the IBM Cloud Command Line Interface, a critical tool for any cloud professional. By the end of this section, you will understand how to manage your infrastructure programmatically and automate your workflows effectively. The IBM Cloud Command Line Interface is essentially a text-based wrapper around the platform's API, providing a predictable way to interact with your resources. While the graphical user interface is helpful for exploration, the command line remains the preferred choice for repeatability and infrastructure as code practices. To get started, you must install the core CLI on your workstation, which enjoys broad support across Windows, macOS, and Linux. This installation acts as a foundational base, but the real power comes from the plugin ecosystem. Because IBM Cloud offers a vast array of services, the base CLI is kept lean to ensure fast startup times and a smaller memory footprint. You install additional functionality, such as support for Kubernetes clusters or container registries, as independent plugins that integrate seamlessly into the main command structure. Before you can issue commands, you must establish an authenticated session with the platform. You typically begin by invoking a login command, which prompts you for your credentials or supports single sign-on mechanisms for enterprise users. Once authenticated, the CLI needs to know where your resources live, requiring you to target a specific region and potentially set a resource group as your default context. Think of this as defining your current working directory in a file system. It prevents you from accidentally modifying resources in the wrong geographical data center. By setting the target correctly, you minimize the risk that comes with manual errors when managing multiple environments. Keeping your context explicit is a disciplined approach that pays dividends once you start managing dozens of distinct resource groups across global regions. Once you are logged in and targeted, the CLI allows you to perform highly granular operations across the IBM Cloud ecosystem. You can provision or terminate virtual server instances, attach storage volumes, and modify networking components like subnets or security groups directly from your terminal. If you find yourself consistently typing long sequences of commands, you can chain these instructions together into shell scripts or integrate them directly into your continuous integration and continuous deployment pipelines. This transition from manual interaction to scripted automation is the hallmark of mature cloud engineering practices. It allows you to treat your infrastructure layout as a version-controlled entity, which makes your deployments not only faster, but also significantly more reliable and easier to audit for compliance requirements. Ultimately, the command line interface removes the abstraction layer between you and the platform, giving you a direct line to your infrastructure. Whether you are troubleshooting a connectivity issue by inspecting security policy definitions or pulling logs from a container registry, the interface provides immediate, structured feedback. It is an investment in your own productivity, especially as the complexity of your cloud projects grows over time. By mastering these terminal commands today, you are preparing yourself to operate at the speed that modern cloud-native architectures demand. Practice is key here, so I encourage you to set up your environment, authenticate, and explore your resource hierarchy using these diagnostic commands. I will see you in the next lecture. Welcome to this lesson on navigating the IBM Cloud Platform. Today, we will focus on maximizing your efficiency within the console interface. The IBM Cloud Console is designed as a centralized hub for managing the entire lifecycle of your cloud resources across global regions and logical containers. When you first log in, the landing page serves as your mission control, providing a visual snapshot of your ongoing deployments and overall platform status. You can customize this dashboard to prioritize the information that matters most to your day-to-day work, such as pinning your most frequently accessed services to the top of your view. Tracking recent resource access is equally straightforward, as the history panel maintains a log of your last visited pages, allowing you to jump back into a configuration task without navigating through deep menu trees. Understanding this landing page structure is essential for maintaining situational awareness, especially when you are balancing multiple projects across different resource groups. By treating the console as a workspace rather than just a storage facility, you position yourself to respond more quickly to changes in your infrastructure. This flexibility is what allows experienced practitioners to spend less time clicking through menus and more time on high-value architecture decisions. Integrating these small navigation habits into your workflow reduces the cognitive load associated with managing complex cloud environments. The navigation menu, typically located in the upper left corner of the interface, follows a hierarchical structure that mirrors the logical organization of the IBM Cloud Platform. It is systematically categorized into infrastructure, platform services, security tools, and billing, which helps in narrowing down exactly where a specific setting resides. If you ever find yourself lost in the submenus, the global search bar at the top of the console is your primary tool for rapid discovery. This search functionality does more than just locate specific resource instances. It also indexes documentation and catalog offerings, making it an excellent resource when you are researching a new service you have not yet provisioned. For those who manage large-scale deployments, the list view of your resources serves as the standard tool for operational oversight. You can organize these views by state, category, or physical location, which is particularly useful when you need to perform bulk actions on a specific subset of nodes. Learning to filter effectively in this view allows you to maintain order even as the number of your provisioned assets grows into the hundreds or thousands. Beyond basic navigation, the console provides embedded tools that simplify administrative duties, most notably within the identity and access management integration. Rather than switching between entirely different portals, you can manage user invitations, define access groups, and manage API keys directly from the context of your resource management workflow. The interface is built to provide these administrative hooks right where you are working, which minimizes the context switching that often leads to configuration errors. Additionally, you will notice that the platform includes cost estimation tools and direct pathways for support ticket creation throughout the experience. These components are surfaced contextually, meaning they appear when you are creating or modifying services, providing immediate visibility into the financial implications of your choices. Having the ability to initiate a support case while viewing the specific resource configuration you are questioning saves significant time and documentation effort. Effectively utilizing these integrated paths signals a level of proficiency that bridges the gap between basic resource deployment and true cloud administration. See you in the next lesson. Hello, and welcome back. Today, we are turning our attention to the foundational layer of IBM Cloud's compute offerings by exploring bare metal servers. This chapter will focus on how these dedicated, non-virtualized resources provide the baseline performance and isolation required for your most demanding enterprise workloads. When we talk about bare metal servers, we are essentially discussing the provision of physical hardware dedicated exclusively to a single tenant. Unlike virtualized environments that rely on a hypervisor to slice physical resources into smaller, multi-tenant virtual machines, a bare metal server places your operating system directly onto the physical hardware. This architectural choice eliminates the overhead associated with hypervisor resource scheduling, effectively ending the noisy neighbor problem where the resource consumption of one tenant inadvertently impacts the performance of another. Because you have raw access to the hardware, you gain total control over the configuration, including the selection of specific processor architectures, high-performance RAM, specialized storage controllers, and dedicated high-throughput network interface cards. This level of granular control is rarely available in abstracted cloud environments, making it a critical choice for organizations that must adhere to strict regulatory compliance standards requiring physical isolation. Whether you are running massive database engines that demand constant, uncompromised I/O throughput, or executing latency-sensitive computational kernels, this service ensures that you are not competing for cycles with other workloads. In terms of operational management, provisioning bare metal servers is naturally more deliberate than deploying a virtual instance because you are interacting with physical infrastructure. While virtualized instances can often be scaled or spun up in seconds, bare metal provisioning times depend on hardware availability and the time required to boot and configure the physical components. You will find that IBM Cloud offers flexible billing cycles, allowing you to choose between hourly billing for short-term projects and monthly options for long-term stable workloads. Configuration flexibility extends to the physical storage layer, where administrators can implement hardware-level RAID to achieve the necessary balance between data redundancy and performance. Furthermore, these servers provide redundant network uplinks, ensuring that your connectivity remains robust even in the event of a physical switch or cable failure. Because you possess firmware-level access, you retain the ability to perform low-level maintenance, such as updating BIOS or managing low-level hardware alerts, which is an essential feature for teams that need to treat their cloud infrastructure with the same rigor as their on-premises data centers. It is important to acknowledge that while bare metal provides unrivaled performance, it inherently trades away the rapid, elastic scalability that define virtualization. You cannot simply adjust the CPU or RAM on a bare metal server with a few clicks. Instead, any upgrade of the physical components generally requires a provisioning of a new server and a migration of data, which is a significant architectural consideration. However, this is largely mitigated by using automation to integrate these servers into your broader infrastructure, where they can serve as the high-performance backbone for your application stack. One common pattern involves using bare metal for the data-intensive parts of the enterprise, such as a back-end SQL cluster or a high-frequency trading engine, while utilizing virtualized instances for the horizontally scalable web or application layers. This hybrid approach allows you to maximize the benefits of single-tenant security postures and custom hardware specifications while still maintaining a degree of agility. By understanding the underlying physics of your infrastructure, you can confidently place workloads where they will perform most efficiently, ensuring that your enterprise architecture is both robust and performant. I will see you in our next session. Hello, and let's dive into the specifics of virtual servers for Classic. This segment examines how traditional compute instances function within the IBM Cloud infrastructure. When we talk about virtual server for classic, we are essentially looking at the infrastructure that predates the modern virtual private cloud architecture. These instances reside in a flat, traditional network environment, which often makes them a preferred choice for organizations migrating legacy workloads that rely on specific networking paradigms. The deployment lifecycle for these servers is quite flexible, allowing you to choose between hourly billing for transient dev test workloads or monthly billing for sustained, steady-state production environments. You have to be deliberate about your performance requirements here, as the choice between public, multi-tenant nodes and dedicated, single-tenant hosts can significantly impact your compliance posture. If you are operating in a highly regulated industry, the dedicated host model provides the isolation necessary to satisfy stringent security audits, even if it comes at a higher price point than standard multi-tenant compute. The storage subsystem for these virtual servers presents a variety of configuration trade-offs that you must navigate. You can utilize local attached storage for high-speed, temporary scratch space, although this data is ephemeral and tied to the life cycle of the instance itself. For persistent data, you would instead attach storage area network persistent storage, which decouples your data from the compute node, ensuring that your files remain available even if the underlying virtual machine is rebooted or replaced. Choosing between these options involves balancing I/O requirements against the need for data durability and network latency. Furthermore, the platform offers different profile flavors, such as balanced, compute-optimized, or memory-optimized configurations, which allows you to right-size the underlying hardware to fit the specific footprint of your application. You are effectively tailoring the CPU to RAM ratio, which is crucial when you are attempting to optimize cost without sacrificing the responsiveness of your software. Networking and security within the classic infrastructure rely on established mechanisms like VLANs and subnet structures, rather than the granular security groups synonymous with modern VPCs. You manage access at the interface layer, and while you have basic load balancing capabilities available, the operational overhead can feel quite different from the software-defined networking you see in newer cloud environments. You are also responsible for selecting the operating system images, and the ability to utilize custom image templates is a key feature for maintaining consistency across a large fleet of servers. This is particularly important for organizations that need to deploy hardened images that comply with corporate security standards. In terms of migration, many companies find that combining classic virtual servers with bare metal options allows them to maintain a hybrid approach that supports legacy architecture while still taking advantage of the surrounding cloud ecosystem. Understanding these classic components is essential because many enterprise environments have not yet moved entirely to a VPC native model. You need to understand how these legacy networks interface with the rest of your cloud resources, especially if you are bridging data between a modern cluster and a classic server. Maintaining traditional operational paradigms requires a firm grasp of how security group attachments and subnetting work in this specific ecosystem. By mastering these details, you ensure that your migration and management strategies remain consistent, regardless of whether you are spinning up a new instance or optimizing an existing long-term deployment. It is about understanding the tooling at your disposal so that you can effectively support the requirements of your application stack without over-provisioning your compute or storage resources. See you in the next lecture. Welcome to our discussion on virtual servers for virtual private cloud, where we will examine the shift from legacy infrastructure models to modern, software-defined environments. This session will ground your understanding of how IBM Cloud reimagines compute provisioning for the modern enterprise. When we examine the transition from classic virtual server infrastructure to the virtual private cloud architecture, we are essentially moving from a shared, multi-tenant network environment to a software-defined, isolated boundary that you control entirely. In the context of the IBM Cloud Platform, this means the underlying hypervisor layers and network stacks are optimized for rapid deployment and higher performance. These virtual server instances are not merely static compute units. They are dynamic entities that exist within a defined subnet, allowing for granular control over IP address management and routing tables. By decoupling the server from the traditional legacy network, IBM provides an environment where provisioning occurs in seconds rather than hours, which is a fundamental requirement for any modern CI/CD pipeline or elastic application lifecycle. This architecture shifts the burden of hardware management away from the consumer, allowing for a focus on the workload rather than the physical topology that supports it. To understand the flexibility of this model, we must consider the instance profile families, which act as templates designed to map specific hardware resources to your workload patterns. IBM categorizes these profiles into compute-optimized, memory-optimized, and balanced categories, ensuring that users do not over-provision resources that their applications do not actually require. For example, a compute-optimized instance might utilize a higher ratio of vCPUs to RAM to support heavy processing tasks, such as batch computation or complex calculations. Conversely, memory-optimized instances ensure that large-scale, in-memory databases have the necessary throughput and capacity to function without swapping to disk, which would otherwise introduce unacceptable latency. Selecting the correct profile is rarely about raw power, but rather about aligning the cost-effective utilization of resources with the specific behavioral characteristics of your software architecture. Integration within the virtual private cloud introduces a sophisticated layer of security and network resiliency that was difficult to achieve in older, flatter architectures. Every virtual server instance must reside within a subnet, which is protected by both security groups and network access control lists. Security groups operate on a stateful basis at the individual instance level, acting as a virtual firewall that tracks established connections and only allows return traffic for authorized requests. Access control lists, however, provide a layer of stateless protection at the subnet level, offering a secondary barrier that can block or permit traffic based on source, destination, and port protocols. This dual-layered approach, combined with the ability to span instances across multiple availability zones within a single region, creates a fault-tolerant mesh that inherently protects against localized data center failures. Lifecycle management for these instances has been fundamentally redesigned to support declarative and predictable operations. You can initiate a state change, such as stopping, starting, or rebooting a server through the API, the command line interface, or the graphical console with immediate effect. Beyond manual intervention, the platform offers auto-scaling groups that monitor metrics such as CPU or memory usage to automatically adjust capacity by provisioning or terminating instances in real time. This dynamic scaling is complemented by features like block storage attachment, which allows persistent data volumes to be mounted to instances as needed, and SSH key injection, which ensures that initial access is handled securely without the risks associated with password-based authentication. The result is an infrastructure model that treats servers as disposable, versioned components rather than long-lived, brittle artifacts that require constant manual tending. See you in our next technical discussion. Welcome back. Let us discuss how managed Kubernetes simplifies container orchestration. When we approach container orchestration, the primary challenge is not the containers themselves, but the maintenance of the environment that hosts them. IBM Cloud Kubernetes Service removes the significant burden of managing the control plane, which includes the master nodes, API servers, and etcd clusters that govern the decision-making process within a cluster. By abstracting this administrative overhead, developers can direct their energy toward deploying applications rather than debugging infrastructure components or wrestling with underlying software updates. This managed approach ensures that the control plane remains highly available and is patched automatically, reducing the risk of security vulnerabilities while ensuring the environment remains current with the latest version standards. Because these components are distributed across multiple availability zones, the architecture inherently protects against localized failures, providing a persistent and stable foundation for services that require high uptime. Beyond the control plane, the management of worker node pools is designed to scale dynamically, regardless of whether you require bare metal performance or the isolation offered by virtual machines. These nodes exist natively within your virtual private network boundaries, which provides a cohesive networking environment that simplifies communication between your application components and existing internal resources. Once these nodes are provisioned, the orchestrator handles the distribution of workloads using intelligent load balancing to ensure that incoming traffic is routed effectively to the pods that are healthiest and least burdened. This abstraction acts as a transparent layer, where the specifics of network topology and physical hardware allocation are handled by the cloud provider, allowing the developer to treat the entire cluster as a unified pool of compute resources ready for consumption. Reliability is further enhanced through declarative configuration manifests, which follow the principle of immutable infrastructure to prevent configuration drift. By defining the desired state of an application in YAML or JSON, you provide the system with a blueprint that it can perpetually compare against the actual state of the cluster. If a container fails or crashes, the self-healing mechanism detects the deviation from the desired state and automatically restarts the process or replaces the instance without human intervention. Similarly, horizontal pod autoscaling monitors resource utilization metrics, such as processor or memory pressure, to dynamically adjust the number of pods running in your deployments. This continuous monitoring ensures that the application always possesses the necessary resources to handle traffic surges while simultaneously optimizing costs during quieter periods. Finally, we must integrate security and lifecycle management into the continuous deployment pipeline to maintain integrity. Modern managed clusters include integrated logging and monitoring solutions that provide visibility into the health of every component, feeding directly into your operational dashboard. Vulnerability advisor scanning is another critical facet, as it periodically reviews the security posture of the images stored in your container registries, flagging issues before they reach production. By pairing these automated security checks with continuous delivery toolchains, you enable a workflow where updates are tested and deployed with extreme consistency. This approach to orchestrated computing is essential for modern technical teams that need to deliver software at velocity while ensuring that the infrastructure remains both secure and highly available for end users. I will see you in the next lecture. Welcome back. In this lesson, we explore Red Hat OpenShift on IBM Cloud, focusing on why it represents perhaps the most robust enterprise-grade Kubernetes offering currently available. Red Hat OpenShift on IBM Cloud is essentially a managed service that takes the complexity of upstream Kubernetes and provides a streamlined, opinionated layer for enterprise production. When you operate a raw Kubernetes cluster, you are effectively acting as your own systems administrator, responsible for patching, networking, and security hardening. With the managed OpenShift service, those operational burdens shift toward the provider, allowing you to focus on the software engineering requirements that actually drive business value. It is essentially an abstraction that enforces best practices through automation, which is why it remains a preferred choice for organizations that simply cannot afford to have their infrastructure management fail. By leveraging this platform, you move away from the fragility of DIY custom-built clusters and toward a supported, battle-tested environment. What makes OpenShift fundamentally different from a vanilla Kubernetes installation is the set of proprietary developer-centric features integrated into the core platform. A prime example is the source-to-image mechanism, which automates the construction of reproducible container images from your source code without requiring you to manually write and maintain complex Docker files for every microservice. Beyond the build process, you gain access to a customized developer console that provides visibility into the application lifecycle that standard Kubernetes dashboards often struggle to surface intuitively. The networking layer is handled through integrated routing mechanisms that manage incoming traffic with greater ease than standard ingress controllers might require in a bare-bones environment. Security is also treated as a first-class citizen here, specifically through security context constraints that enforce strict privilege levels, preventing containerized processes from escalating privileges or compromising the host node unexpectedly. The underlying architecture relies on a clear separation between the control plane and the compute nodes, which are mapped across multi-zone regions to ensure that the infrastructure remains fault-tolerant even if a specific facility experiences a localized failure. This multi-zone deployment strategy is crucial for achieving high availability, as it ensures that the API server and worker nodes are geographically dispersed yet logically unified under a single administrative domain. When the time comes to perform cluster updates, OpenShift provides a mechanism for rolling upgrades that allows you to patch the underlying compute nodes without causing a disruption to the workloads currently running in production. This path for seamless updates is perhaps the most significant operational advantage over self-managed Kubernetes versions, as the orchestration of these upgrades is handled by the platform's internal intelligence. Managing stateful applications and sidecar patterns is further simplified by the embedded operator framework and integrated service mesh capabilities. Operators in this context represent a pattern of codifying the operational knowledge of a human administrator into software that can manage the entire lifecycle of an application. including backup, recovery, and scaling. For complex microservice architectures, the service mesh provides a consistent way to monitor, secure, and connect services, effectively solving the observability challenges that often plague distributed systems. Because these tools are provided as a unified stack, the environment maintains parity between your on-premises clusters and the public cloud instances. This portability ensures that the operational procedures you establish in a private data center remain identical when you transition workloads to the cloud, significantly reducing the cognitive load on your site reliability teams and streamlining your overall deployment methodology. Take care until we meet in the next installment. Welcome to our deep dive into IBM Cloud Code Engine, the cornerstone of serverless execution on the platform. In this session, we will demystify how this platform abstracts infrastructure management while providing robust scaling capabilities for your cloud-native workloads. When we talk about serverless computing, we are essentially discussing an architectural pattern that shifts the responsibility of infrastructure management away from the developer. IBM Cloud Code Engine operates as a fully managed platform that allows you to deploy source code, container images, or batch jobs without manual intervention. Think of it as a logical boundary where you provide the artifacts and the cloud provider handles the underlying deployment and execution environment. You no longer need to worry about provisioning virtual machines, managing cluster nodes, or fine-tuning operating systems to fit your application's profile. This abstraction layer inherently simplifies the operational overhead that often plagues traditional deployment models. By removing these concerns, you gain the freedom to focus entirely on application logic, which is the primary goal of any modern developer. One of the most compelling aspects of Code Engine is its ability to scale seamlessly from zero to massive concurrency. In a traditional server environment, you often have to keep idle resources running to handle potential traffic spikes, which leads to unnecessary cost. Code Engine utilizes dynamic scaling, which ensures that your compute resources match the actual demand in real time. If there is no incoming traffic, your application effectively scales to zero, meaning it stops using active compute capacity entirely. This mechanism is built on top of Knative, which is an open-source Kubernetes-based platform designed to support the deployment and orchestration of serverless, event-driven applications. Because it adheres to these industry standards, you are not locked into proprietary vendor logic, which is a significant architectural advantage. The cost structure of Code Engine is fundamentally tied to the pay-per-execution model, which aligns billing directly with your actual resource usage. Unlike a dedicated server where you pay for capacity regardless of whether it is being utilized, Code Engine charges strictly for the compute and memory consumed during the lifetime of an execution request. This is particularly advantageous for burstable or intermittent workloads, such as data processing jobs that only run for a few minutes once or twice a day. If your code is not running, you are not incurring cost for computing power, effectively eliminating waste. This granular approach to billing turns compute from a fixed overhead into a variable operational expense that scales linearly with your business value. It creates a predictable economic model where your spending directly maps to the real work performed by your services. Integration is an essential trait of modern cloud architecture, and Code Engine excels by supporting diverse event triggers to stimulate your workflows. You can easily connect your applications to HTTP webhooks, incoming message queues, cloud object storage events, or even time-based cron scheduling. When an event occurs, such as a file upload to an object storage bucket, Code Engine can automatically trigger the relevant code execution to process that file in an asynchronous manner. This event-driven design facilitates the creation of loosely coupled microservices that react to the state of the system rather than relying on brittle, synchronous calls. Such architectural patterns make your software significantly more resilient to failures, as each component operates independently within its own lifecycle. You define the rules, and the platform manages the orchestration required to execute the tasks whenever conditions are met. Ultimately, Code Engine functions as an abstraction layer that solves the complexity of modern deployment workflows through automated routing and transparent scaling. Developers can reach the market much faster because there is no need to configure complex load balancing or manual container scheduling logic. The underlying infrastructure effectively disappears from the developer's consciousness, leaving just a clean interface to push code and define constraints. This is highly effective for distributed data processing pipelines where multiple services must coordinate to achieve a specific business outcome. By leveraging this unified deployment target, you ensure that your code behaves consistently across different environments without needing to replicate infrastructure configurations. It represents the logical maturation of cloud computing, where the platform does the heavy lifting, allowing the software to truly flourish as the primary asset. We'll see you in the next lecture. Hello, and welcome back. In this chapter, we explore how object storage operates as a highly scalable paradigm for managing your unstructured data needs. Object storage is fundamentally different from the hierarchical file systems you might be accustomed to in local enterprise environments. Instead of nested folders and directories, object storage utilizes a flat namespace where every piece of data is treated as an individual object, stored alongside its own unique metadata. This structure allows for massive scalability because the system does not need to traverse complex file system trees to locate a specific asset. You interact with this environment through RESTful APIs, which provide a consistent interface for uploading, retrieving, and deleting data regardless of your geographical location. This approach is specifically tailored for multimedia libraries, large-scale backup archives, and the foundation of modern data lake repositories. By decoupling the data from the underlying physical storage hardware, you gain the ability to grow your capacity into the petabyte range without encountering the traditional bottlenecks associated with block-level storage mounting. The economic viability of your storage strategy depends heavily on choosing the correct storage class, as one size rarely fits all requirements. The standard storage class is meant for active workloads where data is accessed frequently, providing high throughput and low latency for your most dynamic files. When your needs shift toward data that is touched less often but must remain available for immediate retrieval, the Vault class provides a more cost-effective alternative. For cases involving long-term retention or regulatory compliance where you might not need to touch the data for potentially years, the Cold Vault class offers the lowest price point at the expense of a longer time to first byte retrieval. Finally, we must consider smart tiering, which acts as an intelligent layer that automatically analyzes your access patterns and migrates objects between these tiers without manual intervention. This removes the operational burden of predicting future data usage while ensuring that your total cost of ownership stays aligned with actual consumption. Managing your data at scale requires more than just picking a tier, as it demands a structured approach to bucket management and lifecycle automation. While the object namespace itself is flat, your organization will likely utilize buckets, which act as logical containers for grouping and securing related objects. Within these buckets, you can leverage metadata tagging to add context to files, allowing for granular searching and auditing that simple file names could never support. Lifecycle policies are perhaps the most vital tool in your arsenal here, as they allow you to define rules that trigger transitions between storage classes automatically. For example, you can set a policy that moves a file from standard to Vault after 30 days and then to Cold Vault after 6 months, ensuring you stop paying premiums for stagnant information. These policies work silently in the background, transforming the management of enterprise data lakes into a predictable, automated process that grows alongside your business requirements. See you in the next lecture. Welcome back. In this lesson, we will focus on the architectural resiliency paradigms of cloud object storage and how data integrity is maintained at scale. When we talk about the resiliency of object storage, we are fundamentally discussing how to decouple data persistence from the fragility of individual physical hardware. At its core, object storage does not rely on traditional RAID controllers or the simple mirroring of files across two identical hard drives, as these methods fail to scale to the exabyte levels required by modern cloud providers. Instead, the architecture employs a sophisticated process of fragmentation, where incoming data is broken into smaller logical segments that are then encrypted for security before they ever touch physical media. Once the data is fragmented and encrypted, it is dispersed across a distributed system of storage nodes. This ensures that no single server or rack constitutes a potential point of failure for the entire object. By spreading these fragments, the system can reconstruct the original file even if multiple components of the physical infrastructure suffer a catastrophic failure. To achieve this level of durability without the unsustainable costs of full duplication, IBM Cloud utilizes information dispersal algorithms, primarily through techniques known as erasure coding. Rather than cloning a file, which would essentially double your storage cost for every piece of information, erasure coding breaks a file into fragments and generates parity pieces based on a mathematical formula. Consider a file divided into 5 data pieces and 3 parity pieces, totaling 8 fragments scattered across different drives. As long as any 5 of those 8 fragments are available, the object can be mathematically reassembled instantly. This provides a robust guarantee of data integrity that is significantly more efficient than full replication while still providing protection against localized hardware outages. The complexity of these calculations is offloaded to the storage controller, which handles the orchestration of these fragments in a way that remains transparent to the end user. The physical placement of these dispersed fragments is what we define as the resiliency level. A single data center deployment keeps these fragments within a restricted proximity, which is appropriate for low-latent, non-critical workloads where hardware failure is the only major threat. However, for enterprise-grade applications, we move toward regional deployments that distribute fragments across multiple availability zones within a single geography. Each zone operates independently with its own power, cooling, and network connectivity, meaning that even a total facility blackout will not result in data loss. For global mission-critical applications, we utilize cross-region deployments, which scatter fragments across entirely separate geographic locations. This strategy maximizes fault tolerance, protecting your data against regional-scale disasters like fires, floods, or major infrastructure failures that might strike a specific part of the world. In considering these storage choices, one must also account for read-write consistency models and the recovery metrics that define your business requirements. Consistency in a distributed object store generally follows the principle of strong consistency for read-after-write operations, ensuring that once you receive an acknowledgement that a file is stored, any subsequent read operation will return that exact byte-perfect version. Regarding disaster recovery, storage resiliency directly dictates your recovery time objective and recovery point objective. By opting for higher resiliency levels, you fundamentally lower the probability of data loss, effectively bringing your recovery point objective towards zero. Furthermore, for highly regulated environments, the configuration of immutability locks provides the final layer of defense by preventing any modifications or deletions for a defined, immutable period. This prevents both malicious activity from bad actors and accidental human error from permanently affecting your data state. See you in the next lecture. Welcome back. And today, we turn our attention to the storage mechanisms that allow our compute instances to function under heavy transactional pressure. We are exploring the features of block-level storage, which plays a pivotal role in maintaining the state of your infrastructure. At the core of modern cloud-native architecture, block storage represents a raw block device mapped directly to a virtual machine or bare metal server as a local disk. Unlike object storage, which handles unstructured data via an API, block storage is treated by the operating system as a traditional drive, supporting standard file systems like NTFS, Extension 4, or XFS. This direct attachment is critical for applications that require low latency and high-performance random read and write operations. When you're deploying a relational database cluster, such as PostgreSQL or MySQL, you require the consistent performance characteristics that only block-level access can reliably provide. It effectively serves as the persistent foundation for operating system boot volumes where speed and data integrity are non-negotiable requirements for the uptime of your service. To balance the conflicting demands of cost and performance, IBM Cloud provides distinct tiering options for block storage that allow precise alignment with workload profiles. Endurance tiers are designed for general-purpose workloads, where the IOPS are predefined based on the total storage capacity provisioned for the volume. This creates a predictable performance model that fits many standard business applications without requiring complex tuning. Conversely, performance tiers offer a much higher degree of granularity, allowing you to explicitly allocate custom IOPS values to match the specific and often stringent demands of an application. By decoupling storage capacity from performance throughput, you gain the flexibility to provision exactly the amount of IOPS required for high transaction environments, ensuring you are not over-provisioning resources while still meeting critical performance level agreements. The underlying physical infrastructure is engineered for speed, utilizing advanced solid-state drive technology and non-volatile memory express protocols to eliminate traditional storage bottlenecks. NVMe, in particular, optimizes the communication path between the storage volume and the CPU, allowing for massive throughput and significantly lower latency than traditional SATA-based SSD structures. This hardware-level optimization is invisible to the application, but translates into immediate improvements in database query completion rates and rapid boot times for virtual machine instances. When multiple throughput-heavy operations occur simultaneously, the low latency characteristic of this infrastructure ensures that the storage layer does not become a point of contention. This reliance on high-performance media is what allows these volumes to serve as the backbone for demanding transactional file systems that require immediate confirmation of write operations. Beyond raw speed, the resiliency and lifecycle management features integrated into the platform are what make this solution truly enterprise-ready. Administrators can take point-in-time snapshots of their volumes to preserve state, which serves as a highly efficient mechanism for data protection and system recovery. If you need to scale your infrastructure, you can clone existing volumes to instantiate new servers with identical configurations, significantly simplifying the deployment of complex, multi-tier application architectures. For disaster recovery scenarios, asynchronous replication allows you to mirror your data across different regions, ensuring that your stateful data can be recovered even in the event of a broad regional outage. Furthermore, you can dynamically resize your volumes as your data consumption grows, often performing these modifications without requiring application downtime or significant re-architecting of the attached server environment. Security remains a primary concern in any cloud deployment, and block storage accounts for this through natively integrated transparent encryption. Every byte written to the disk can be encrypted at rest, ensuring that data is never stored in a readable format on the physical media should it ever be decommissioned. You have the flexibility to choose between provider-managed encryption keys, where the cloud platform handles the lifecycle of the key, or customer-managed keys via a dedicated key management service. This latter option provides you with complete oversight and control, enabling you to rotate or revoke access to your data at any time without involving the cloud service provider. Integrating these security features into the volume itself creates a robust layer of protection that operates independently of the guest operating system, securing your data from the moment it is committed to the disk. I will see you in our next session. Welcome back. Today we examine file storage, a critical architectural component for shared, hierarchical data access in the cloud. When we design systems that require multiple compute instances to interact with a common set of files, a NAS, or network-attached storage model becomes the logical choice. IBM Cloud File Storage provides a high-performance, network-attached storage solution that communicates via the standard Network File System, or NFS protocol. Unlike block storage, which provides raw disk volumes to a single instance, file storage introduces a file system layer that allows for concurrent mounting from multiple virtual server instances. This capability is essential for distributed web server clusters, where each node needs to serve the same set of static assets, or in content management systems where files must be accessible across the entire application tier. The performance profile of these file shares is managed through predefined endurance tiers or custom IOPS configurations, allowing you to align your storage throughput with the specific demands of your workload. By abstracting the hardware, the service ensures that your infrastructure maintains a consistent, hierarchical directory structure, enabling standard file manipulation techniques across all attached compute resources. In terms of operational configuration, mounting an IBM Cloud File Storage volume requires specific network prerequisites, primarily ensuring that the compute instances reside within the appropriate networking context to reach the storage endpoint. Once the NFS mount is established, you are essentially dealing with a remote disk that behaves like local storage but is managed via network protocols. Managing subdirectories and file-level access controls becomes a function of the underlying file system permissions combined with the security groups or access control lists you define at the infrastructure level. Because multiple compute instances might write data simultaneously, it is crucial to understand the implications of file locking and consistency. You must plan for snapshot scheduling, which serves as a robust mechanism for data recovery and integrity management. effectively mitigating the risks associated with accidental deletion or corruption. These snapshots operate seamlessly in the background, providing a point-in-time recovery without disrupting the active file operations being performed by your application tier. Scalability remains a primary concern in modern architecture, and file storage addresses this by allowing you to expand your file system capacity dynamically as your data requirements grow. This is particularly important for high-performance computing clusters that require large repositories of datasets to be shared across many nodes, where running out of space could stall complex jobs. As you scale, the security posture must remain consistent, moving from the initial setup to a mature, geographically distributed storage strategy that maintains data integrity predictable and reliable. The orchestration of this storage across different cloud regions or zones requires a careful approach to network latency and data consistency models. Whether you are building a simple multimedia repository or a massive distributed database, the ability to mount the same storage volume to multiple disparate compute instances serves as the foundational glue for these architectures. By treating file storage as a managed, high-availability service, you offload the maintenance burden of a traditional on-premises filer while retaining the familiar interface of standard directory hierarchies. See you in the next session. Welcome back. In this session, we will examine the IBM Cloudant NoSQL database, a managed service built to handle complex JSON data at scale. Cloudant is fundamentally a fully managed, distributed NoSQL document database, which means you do not have to worry about the underlying infrastructure or manual server maintenance. Because it is natively engineered as a JSON store, it excels when your application data does not fit into the rigid, tabular structure of a traditional relational database. If your schema changes frequently, for example, when you are iterating on a product prototype or dealing with heterogeneous sensor data, Cloudant allows you to store those documents without performing costly table migrations. This flexibility is complemented by its ability to handle heavy transactional workloads, making it a common choice for enterprise applications that need high availability and low latency at the same time. The database is built on the Apache CouchDB architecture, which introduces the concept of a masterless replication model that is significantly different from the primary replica models you might be used to in other engines. The masterless architecture is one of the most critical aspects of Cloudant because it allows for multi-active configurations where any node in a cluster can accept both read and write operations. In a traditional database, you might worry about write locking your primary instance, but with a distributed JSON store, your writes are partitioned and replicated across different nodes. This design inherently provides high availability because the system does not designate a single point of failure that would require a manual failover process during a regional outage. Through this peer-to-peer replication protocol, data is synchronized across geographically distributed database clusters, ensuring that your users, whether they are in London or Singapore, can access their data with minimal latency. Because this synchronization happens natively, the database remains resilient even when individual nodes or entire data centers become temporarily unreachable. Interaction with the database happens primarily through a RESTful API, which aligns well with modern web and mobile development practices. When you need to retrieve data, you can use basic key-based lookups, but Cloudant also supports more sophisticated querying methodologies. One traditional way to process data is through MapReduce views, where you pass a function to the database to transform and aggregate data on the fly. However, you can also utilize Cloudant Query, which uses a more intuitive JSON-based syntax to perform lookups similar to SQL filters without the complexity of writing custom MapReduce logic. For more advanced requirements, the database engine natively embeds full-text indexing and geospatial search functionalities, allowing you to run complex searches against your documents without moving the data into an external search engine. When it comes to operations, Cloudant uses a provision capacity model where you define the throughput in terms of lookups, writes, and queries per second. This flexibility allows you to right-size your database performance based on your current budget and traffic demands rather than paying for idle hardware. Backup and restore paradigms are also built into the service, allowing for continuous snapshots that protect your data against accidental deletion or corruption. Because the service is multi-tenant by design, but allows for dedicated environments when compliance or performance isolation is required, it fits into a wide variety of architectural patterns. You can easily integrate Cloudant with serverless compute functions, creating an event-driven architecture where a change in a database document automatically triggers a cloud function to perform downstream processing. This integration capability is vital for mobile application synchronization and edge computing use cases. In disconnected mobile scenarios, Cloudant provides the ability to store data locally on a device and synchronize it with the cloud only when connectivity is restored, which is facilitated by the same replication protocol used between cloud nodes. Because the synchronization process is smart enough to handle conflicts programmatically, developers can focus on the user experience instead of writing repetitive network handling code. From a security standpoint, the service encrypts data both at rest and in transit, and you manage access through the standard identity and access management integration used across the broader cloud platform. By combining this robust architectural foundation with seamless global synchronization, the database enables developers to build global-scale applications that are resilient, scalable, and secure. I will see you in the next lesson. Welcome to our focus on storage selection strategies, where we examine the technical constraints and requirements that drive architectural decision-making. We will navigate the trade-offs inherent in choosing the optimal storage medium for your enterprise workloads. In the realm of cloud design, selecting the right storage is not merely a matter of picking a random service, but rather a methodical evaluation of access patterns, durability requirements, and performance boundaries. When we assess block storage, we are effectively talking about providing low-level, high-performance, persistent disk space directly to a compute instance. This is the optimal configuration for database engines that necessitate rapid, read-write intensive operations where latency must remain strictly minimized. Because block storage behaves like a physical hard drive attached to a local machine, it manages the file system locally, which makes it unsuitable for multiple server instances trying to write to the same space simultaneously. If you try to force a different type of storage into a high-throughput transaction role, you will quickly find that the overhead of network protocols or software-defined layers introduces unacceptable delays. Architectural integrity relies on matching the right hardware abstraction to the specific demands of the underlying application software. When your architecture shifts towards shared application clusters or legacy enterprise file systems, standard block storage becomes an inhibitor rather than an enabler. This is where file storage enters the picture, providing a hierarchical storage structure reachable over a network, typically via the network file system protocol. Unlike block-level devices, file storage simplifies collaboration between multiple virtual instances by maintaining a centralized mount point that persists state data independently of individual server lifecycles. Think of this as the digital equivalent of a shared office filing cabinet where multiple employees simultaneously read and contribute documents. It is structurally designed to handle concurrent access, making it the most sensible choice for content management systems or home directory services that do not require the raw, granular speed of a block device. Using a network-attached file system allows for seamless scaling of the compute layer without needing to reconfigure the actual data repository every time a new node joins the cluster. Object storage represents a distinct paradigm, prioritizing massive scalability and accessibility over the low-latency performance of disks. By treating every piece of data as an object coupled with metadata, this storage type is ideal for unstructured datasets, such as media backups, log archives, or static asset distribution. Because it lacks a traditional directory hierarchy, it excels at retrieving data via flat namespaces, often triggered through simple RESTful APIs or standard web protocols. When an organization attempts to use block storage for massive, long-term archiving, they commit an anti-pattern that bloats their total cost of ownership by paying for high-performance IOPS that remain largely idle. Object storage allows you to balance cost and performance by leveraging lifecycle policies that can automatically move data to archival tiers when it is no longer frequently accessed. This ensures that you maintain the durability of the data without inflating your operational budget on resources that do not actually improve the application's efficiency. Beyond the basic silos of file, block, and object, we encounter specialized NoSQL databases like Cloudant that integrate a different philosophy entirely. These systems shift the focus away from the underlying storage infrastructure and toward the model of the data itself, providing a flexible schema that adjusts as your information evolves. In a schemaless or document-oriented database, The physical storage concerns are abstracted away from the developer, and the engine focuses on indexing and retrieval patterns that a standard file system simply cannot offer. When evaluating these options, you must scrutinize your input-output operations per second metrics and target latency values, as these clarify whether your workload is compute-heavy or storage-bound. True architectural mastery involves understanding these metrics deeply enough to identify potential bottlenecks before a single line of infrastructure as code is deployed. By systematically evaluating your structural requirements against these storage tiers, you ensure that your design remains performant, cost-efficient, and structurally sound throughout the full transition of your project lifecycles. I will see you in the next lecture. Welcome back. Let's explore the architectural foundations of virtual private cloud networking. When we talk about a virtual private cloud, or VPC, we are essentially moving away from the loose, shared infrastructure of classic networking and into a world of software-defined control. Think of a VPC as a logically isolated segment within the public cloud where you exert absolute authority over your own network topology. In a traditional data center, you might have spent weeks racking and stacking hardware to achieve network isolation. Here, that same isolation is achieved through software policies and logical boundaries. This allows you to place your compute resources, such as virtual server instances or container clusters, in an environment that is invisible to the rest of the public internet unless you explicitly decide otherwise. By definition, a VPC provides a dedicated network environment that behaves as if it were on-premises, yet it retains all the elastic benefits of the cloud. You control the IP address ranges, the creation of subnets, and the definition of route tables that govern how traffic moves within your environment. It is the bedrock upon which secure, modern cloud-native applications are built, ensuring that your intellectual property remains protected within your defined perimeter. To understand the mechanics of this isolation, we must first look at how we address these networks using standard classless interdomain routing, or CIDR blocks. When you create a VPC, you are effectively reserving a slice of private IP space that you manage entirely on your own terms. This CIDR block provides the necessary address prefix from which you will later derive your individual subnets. Proper planning at this layer is critical because once you define the size of your address block, changing it in a live production environment becomes a complex architectural hurdle. I always suggest selecting a prefix that provides enough headroom for future expansion without overlapping with existing corporate networks you might connect later via a VPN or direct link. By segregating these resources into their own isolated spaces, you ensure that traffic can be filtered, monitored, and logged according to your specific compliance requirements. Every resource that gains a presence inside your VPC must adhere to the rules defined at this foundational architectural level. Beyond simple addressing, a VPC introduces the concept of multi-zone architecture, which is pivotal for building resilient systems that survive individual data center failures. Within the IBM Cloud ecosystem, VPCs span regions, and within those regions, you can distribute your subnets across multiple availability zones. This design ensures that if one zone experiences a physical outage, your workloads can continue to function in another zone without losing network connectivity. The software-defined nature of the VPC allows for rapid provisioning, meaning you can spin up entirely new network segments in minutes rather than months. As your business scales, your network scales with it, allowing you to attach block storage, manage load balancing, and attach secure internet gateways with high predictability. This horizontal scaling capability is what distinguishes professional cloud engineering from legacy, static networking models, where capacity was perpetually capped by hardware limitations. You gain an agile, programmable network that responds to demand dynamically, all while maintaining a consistent security posture across the entire application stack. Integration with other IBM Cloud infrastructure components is seamless when you adopt the VPC model for your application deployments. Your compute nodes, whether they are virtual servers or Kubernetes clusters, sit within these subnets and gain high-speed private connectivity to other native cloud services. You can attach load balancers to distribute incoming traffic efficiently and use virtual private endpoints to access storage services without ever traversing the public internet. This architecture inherently prioritizes a security-first approach, where the default state is denial of all traffic unless specific routing and access policies are established. By strictly controlling the gateway services and internal routing policies, You create a robust perimeter that is both performant and auditable. This design consistency allows your teams to deploy environments that behave identically in development, staging, and production. Ultimately, this approach removes the ambiguity of network maintenance and allows developers to focus on building features rather than wrestling with physical infrastructure logistics. I will see you in the next lecture. Hello and welcome back. In this lesson, we will explore the fundamentals of subnet architecture within the IBM Cloud Virtual Private Cloud environment. When we talk about subnets in the context of cloud architecture, we are essentially discussing the mechanism for partitioning your larger virtual private cloud address space into smaller, logically isolated segments. Think of a virtual private cloud as your own private plot of digital land, while a subnet is the internal fencing that dictates which machines can communicate directly with one another. Each subnet belongs to exactly one availability zone, which is a critical design constraint to remember when planning for high availability or disaster recovery. By confining a subnet to a single zone, we gain predictable latency and a clear understanding of the blast radius if an individual data center experiences a failure. This structural organization is not merely a suggestion. It is a foundational requirement for deploying compute resources natively and securely within the IBM Cloud. The mathematical reality of these subnets is dictated by classless interdomain routing, where you assign specific CIDR blocks to define the range of private IP addresses available to your resources. One of the most important decisions you face when designing this network topology is the choice between public and private subnet configurations. A public subnet is characterized by its ability to route traffic to and from the public internet, usually facilitated by a public gateway associated with that specific subnet. Conversely, a private subnet remains entirely isolated from any direct inbound internet traffic, which is a significant advantage for security-sensitive workloads like database backends or internal application servers. By isolating these resources, you effectively reduce the attack surface, ensuring that only authorized traffic arrives through pre-configured load balancers or bastion hosts. Security in this context is improved not by complex perimeter defenses alone, but by the thoughtful segmentation of your application tiers. When your database exists in a dedicated, private, non-routable subnet, you eliminate the possibility of a direct external compromise, forcing malicious actors to navigate multiple layers of infrastructure to reach your most sensitive data. Effective subnet architecture also requires rigorous capacity planning to avoid the pitfalls of overlapping address spaces, particularly as environments scale or connect to other VPCs. When you design your IP addressing strategy, it is tempting to use broad, default ranges, but this often leads to routing conflicts that are notoriously difficult to debug later in the project lifecycle. You must calculate your subnet requirements based on the number of projected compute instances needed for each tier, allowing for future growth without exhausting the available private IPs within the segment. If you fail to manage these constraints early, you may find yourself readdressing entire VPCs, which is an operation that almost always involves significant downtime or complex service migrations. Maintaining an accurate inventory of assigned blocks across all your interconnected environments ensures that your network remains predictably managed as you scale from a single development environment to a global enterprise footprint. This consistency is the difference between a resilient, automated infrastructure and a fragile one that requires manual, error-prone interventions. Beyond basic connectivity, the primary goal of this logical partitioning is to secure your applications through a tier-based deployment strategy. A typical robust architecture maps individual subnets to specific roles, such as placing your web-facing load balancers in a public subnet while moving the business logic to an application tier and the data storage to a dedicated, restricted database tier. This deliberate segmentation prevents lateral network movement, which is the process where a compromised web server might be used to probe or attack internal resources. By controlling the flow of traffic at the subnet level, you create a granular security posture that effectively minimizes the blast radius of any individual service failure or security breach. This approach allows you to deploy and scale your resources dynamically, knowing that your security boundaries are enforced natively by the cloud provider's infrastructure components. When you implement these tiers carefully, you achieve a level of operational efficiency that allows for seamless updates and maintenance, as you can replace entire tiers of your application without impacting the connectivity or security requirements of the underlying infrastructure components. I will see you in the next lecture. Welcome to our deep dive into security groups, the foundational stateful firewalls for your IBM Cloud VPC environment. We will explore how these virtual constructs provide granular traffic control at the network interface level. In the landscape of cloud-native networking, security groups act as the primary gatekeepers for your virtual server instances. Unlike broader network controls that might operate at the subnet level, a security group is attached directly to the virtual network interface of a specific server. This proximity allows for a highly granular approach where you can define exactly what traffic is permitted to reach a specific compute resource. Because these are stateful virtual firewalls, the mechanism tracks the state of active connections, which allows return traffic for established flows to pass through without needing a corresponding explicit rule. Such a design choice significantly simplifies the configuration overhead that often plagues stateless architectures, where one would typically have to manually manage both inbound and outbound rules for every single conversation. This automatic tracking of connection states ensures that as long as the initial request is permitted based on your rules, the response is handled with the efficiency and intelligence we expect from modern infrastructure. The baseline behavior of a security group is defined by an implicit deny-all stance for all inbound traffic upon provisioning. You essentially start with a clean slate where nothing is allowed until you explicitly define a rule that says otherwise. Conversely, security groups in IBM Cloud generally permit all outbound traffic by default, facilitating immediate connectivity for your workloads to reach external services or internal resources as needed. This robust default security posture ensures that your instances are not exposed to the public internet by mistake the moment they are deployed. When you do need to open an inbound path, you are not just limited to static IP ranges. You can specify rules based on transmission control protocol or user datagram protocol ports. This specificity is crucial for managing services like web servers that require port 80 or 443 or remote administrative access channels that might reside on other specific ports. Moving beyond simple IP-based filtering, these security mechanisms allow the referencing of other security groups as dynamic sources of traffic. This is a powerful abstraction that enables elastic scaling without the need to update your firewall rules every time an IP address changes due to a scaling event. Imagine you have a web tier and an application tier. Instead of hard-coding the IP addresses of your web servers into the application server's security group, you simply create a rule that permits traffic originating from the web server's security group ID. As new instances are added to the web tier, they automatically inherit the security group tagging and are immediately trusted by the application tier, ensuring that your security configuration remains dynamic and consistent. This capability is instrumental in managing complex architectures where global scaling and rapid service deployment are standard operational requirements, as it maintains connectivity without the manual friction of update cycles. Configuration of these rules is handled through CIDR blocks for broader network ranges, but the ability to target individual ports adds the precision required for production environments. You can manage these settings centrally via the IBM Cloud control plane, ensuring that your security posture is consistent and verifiable at any scale. The evaluation of these rules happens instantaneously upon receipt of a packet, providing high-performance filtering that does not introduce unnecessary latency to your application traffic. By abstracting the complexities of low-level network packet filtering into a manageable, policy-driven interface, IBM Cloud enables architects to focus on the intent of their security policies rather than the mechanics of rule application. As you progress, keep in mind that the primary value here lies in the stateful nature of these groups and their ability to dynamically scale with your virtual infrastructure fleet. See you in the next lecture. Hello, and welcome back. Today we are exploring access control lists as a fundamental architectural component within IBM Cloud, virtual private clouds. In this lesson, we will examine how these stateless firewalls serve as the primary defensive perimeter for subnet-level traffic management. Access control lists, or ACLs, function as stateless packet filters that operate at the subnet boundary by evaluating every single datagram entering or leaving that specific network segment. Unlike stateful security groups that dynamically track connection states, An ACL treats every packet as an independent event without any inherent memory of previous traffic flows. Because they are stateless, you must define explicit rules for both inbound and outbound traffic to facilitate bidirectional communication. If you allow a client to request data from a server, the ACL will implicitly block the return traffic unless you manually create a corresponding rule to permit that response packet. This necessity for reciprocal rule definitions increases the administrative burden, requiring precision and constant vigilance to ensure that legitimate application traffic is not inadvertently dropped by a restrictive entry. The evaluation logic employed by these lists is strictly sequential, meaning the order of your defined rules dictates the outcome of the filtering process. Each rule is assigned a unique numerical index, and the system processes these rules starting from the lowest number and proceeding toward the highest value. The fundamental mechanism here is a first match paradigm, where the engine stops evaluating as soon as it encounters a rule that matches the packet attributes such as source, destination, protocol, or port range. Once this first match occurs, the associated action, either allow or deny, is applied immediately, and all subsequent rules are ignored regardless of how specific they might be. This behavior places a heavy responsibility on the administrator to ensure that highly specific rules are placed at the top of the list, while catch-all default policies reside at the end. By operating at the subnet boundary, ACLs provide a robust, macro-level defense mechanism that is particularly effective as the first line of security against volumetric threats, such as distributed denial of service attacks. When an influx of malicious traffic is identified, you can implement a deny rule at the top of your ACL, effectively discarding that traffic before it ever initiates a connection attempt with individual virtual server instances. This layered approach creates an efficient defense in-depth architecture where the ACL acts as the coarse-grained gatekeeper, while stateful security groups perform fine-grained filtering closer to the compute resources. By offloading the initial packet inspection to the subnet boundary, you reduce the processing overhead on the virtual interface of the underlying hypervisor. This combined deployment strategy ensures that your cloud infrastructure remains resilient, predictable, and protected against both external scanning and large-scale packet floods. Maintaining these lists requires a disciplined approach to configuration management to avoid the common pitfall of rule clutter or conflicting directives. Since every packet is inspected synchronously as it traverses the boundary, any misconfiguration or overlapping rule set can lead to unintentional connectivity outages that are often difficult to troubleshoot. You should adopt a policy of least privilege, explicitly granting only the communication flows necessary for service operation and defaulting to a deny-all stance for any traffic that has not been explicitly authorized. Because the system lacks a state table to track established connections, you must carefully calculate the ephemeral port ranges used by your applications when crafting inbound and outbound rules for TCP or UDP traffic. Effective management necessitates regular audits of your rule lists to remove orphaned entries and ensure that the ordered sequence remains logically consistent with the evolving requirements of your production workloads. See you in the next lecture. Hello, welcome back. Today, we will explore the foundational mechanics of cloud load balancers as a cornerstone for building highly available systems. In any distributed architecture, the primary challenge is to manage incoming traffic streams across multiple compute instances effectively. Relying on a single entry point creates a single point of failure that fundamentally contradicts the goal of resilient cloud infrastructure. Load balancers act as the traffic distribution layer, sitting between the end user and your backend resources to ensure no single instance is overwhelmed. By distributing requests across a pool of healthy targets, these mechanisms improve overall responsiveness and prevent the service degradation that often follows resource exhaustion. Achieving this requires a combination of intelligent routing policies and automatic recovery processes that function behind the scenes. This level of abstraction allows developers to focus on application logic while the cloud provider maintains the consistent delivery of requests regardless of underlying volatility. When implemented correctly, these services provide a seamless and uninterrupted experience even when individual components fail or require reprovisioning. When we shift our focus to the application layer, or layer 7, we gain the ability to make routing decisions based on granular data. Application load balancers evaluate the contents of the request itself, such as the specific URL path, host header, or custom HTTP headers to direct traffic to the most appropriate microservice. This is particularly relevant in complex environments where different segments of an application are deployed as discrete containers or serverless functions. By intelligently routing based on semantic information, you can decouple your infrastructure from your application logic, allowing for independent scaling of services. This capability is essential for modern, API-centric architectures, where a single domain might serve fundamentally different functions depending on the requested resource. The overhead associated with analyzing the application layer is a necessary trade-off for the increased control and flexibility these intelligent proxies provide. In contrast to application-level intelligence, network load balancers operate primarily at layer 4, focusing on raw performance and high throughput. These components manage TCP and UDP traffic at the transport layer, where the primary objective is to move data across the wire with minimal latency. Since these balancers do not need to parse or inspect the HTTP body or application headers, they can handle millions of requests per second with extreme efficiency. This makes them the ideal choice for high-volume streaming, gaming, or real-time data ingestion scenarios where sub-millisecond latency is the governing constraint. They scale automatically to meet demand, providing a predictable and stable entry point for your network traffic regardless of whether that traffic is transient or constant. Choosing between a Layer 7 and a Layer 4 load balancer is a classic architectural trade-off that should always be informed by your specific latency and inspection requirements. The invisible glue that holds all of these load balancing configurations together is the concept of health checks. A load balancer is only as effective as its ability to verify the status of the targets it governs by actively polling endpoints. By sending periodic probe requests, the system can determine if an instance is responsive or if it has entered a degraded, unhealthy state. Should an instance fail to respond correctly within the defined threshold, the balancer dynamically removes it from the routing pool, routing traffic away from the faulty component immediately. When the instance eventually recovers or is replaced by an automated scaling group, the health check process detects the restoration and adds it back into the rotation without manual intervention. This cycle of automatic detection and remediation is the critical feature that transforms manually deployed clusters into self-healing, fault-tolerant ecosystems. I look forward to seeing you in our next session. Welcome back to our exploration of cloud networking architectures. In this session, we investigate how you can bridge on-premises environments with the cloud via direct link and how you can optimize asset delivery globally using content delivery networks. When we talk about IBM Cloud Direct Link, we are essentially discussing the mechanism to bypass the unpredictability of the public internet. By establishing a dedicated private network connection between your on-premises infrastructure and the IBM Cloud environment, you gain a level of reliability and latency control that is impossible to achieve over standard internet routes. This is particularly relevant for hybrid cloud architectures where your corporate data center needs to act as a seamless extension of your cloud footprint. From an architectural perspective, this usually involves a physical cross-connect in a co-location facility, effectively extending your internal network into the cloud provider's backbone. By doing so, you ensure that high-bandwidth data transfers, such as large database migrations or intensive backup operations, occur over a private pathway. This eliminates the contention and variable performance associated with transit across internet service providers. When you architect for mission-critical applications, this predictability becomes a non-negotiable requirement for operational success and compliance. Relying on such private connections allows you to standardize your egress and ingress traffic patterns, which is a fundamental requirement for maintaining consistent application performance in a complex hybrid configuration. Transitioning from connectivity to global distribution, we must look at how content delivery networks, or CDNs, function as an edge caching layer for your application assets. Instead of forcing every end user to interact with your origin server, a CDN leverages a geographically distributed network of servers to cache static content like images, style sheets, and scripts physically closer to the user. When a request hits the edge, the CDN determines if a valid cached copy exists, effectively offloading that request from your origin. This mechanism contributes significantly to reducing latency and improving the overall end-user experience, as travel time for data packets is minimized. Furthermore, This approach drastically reduces the bandwidth consumption on your primary infrastructure, allowing your origin servers to focus on dynamic processing rather than serving static assets. You configure these distributions by setting appropriate time-to-live values, which dictate how long a piece of content remains valid in cache before the edge node fetches a fresh copy from the origin. This balance of cache management ensures that your global audience sees updated content while still reaping the performance benefits of edge delivery. Beyond mere performance, the modern CDN serves as a critical perimeter security component for your cloud architecture. By sitting in front of your origin, global CDNs provide a natural barrier against common internet threats, such as distributed denial of service attacks. The distributed nature of the edge network allows for the absorption and filtration of malicious traffic before it ever reaches your virtual private cloud or host environment. When integrated with web application firewalls, the CDN can inspect incoming requests against security policies, blocking suspicious patterns or unauthorized requests at the point of entry. This layer of security is essential for protecting your web-facing assets while maintaining the high availability that modern applications demand. Effectively managed, these layers work in tandem to provide a robust, resilient surface area that can withstand increased traffic spikes and security disruptions. Whether you are scaling an enterprise application or managing global media content, these configurations verify that your services remain performant and shielded from the inherent risks of the public web. Until the next lecture. Welcome to our exploration of identity and access management in the IBM Cloud. In this chapter, we will dissect the centralized security framework that governs how users and applications gain access to our infrastructure. Identity and access management, often abbreviated as IAM, is the fundamental security layer that determines who can perform what actions within your cloud environment. It acts as the gatekeeper, ensuring that only authenticated entities are granted access to specific resources based on the principle of least privilege. Unlike physical security, where access is controlled by keys or badges, Cloud IAM relies on digital identities verified through a centralized authority. This authority manages the entire life cycle of an identity, from creation and authentication to authorization and eventual decommissioning. By centralizing these controls, IBM Cloud allows architects to maintain a consistent security posture across disparate applications, virtual servers, and storage volumes without creating silos of identity management that are difficult to audit. Authentication is the first pillar of this framework, representing the process of confirming an entity is who they claim to be. While simple usernames and passwords might suffice for local testing, production environments require more robust mechanisms like multi-factor authentication to mitigate risks associated with credential theft. IBM Cloud IAM supports federation, which is particularly useful when you already have an existing enterprise directory like Microsoft Active Directory. By establishing a trust relationship between your local directory and the cloud provider, you allow users to authenticate using their familiar corporate credentials. This approach simplifies user management and ensures that when an employee leaves the organization and their account is deactivated in your local directory, their access to the cloud environment is revoked instantaneously, reducing the surface area for potential security breaches. Once an identity is authenticated, the next concern is authorization, which governs what that individual or service is allowed to do. Instead of assigning permissions to every individual user, which would quickly become an administrative nightmare, we use access groups. You can think of an access group as a container for users and service IDs that share the same functional role within your organization. When you apply a policy to an access group, every member of that group inherits those permissions immediately. This strategy is critical for preventing configuration drift, a phenomenon where manual, inconsistent changes lead to different permission levels for users who should theoretically hold the same administrative standing. By managing access through these groups, you ensure that administrative overhead remains low and that security policies are applied consistently across your entire infrastructure. Programmatic access is another vital aspect of IAM that requires specific attention, especially for automated workloads and microservices. For these scenarios, we utilize service IDs, which act as identities for non-human entities like scripts or applications running on the cloud. A service ID can be assigned an API key, which serves as a long-lived credential for the application to authenticate against IBM Cloud services. Managing the lifecycle of these API keys is a mature security practice that you must implement to ensure longevity and safety. You should regularly rotate these keys and monitor their usage patterns to detect any anomalies. If an application is compromised, having the ability to quickly invalidate a specific service ID's API key without impacting the rest of your fleet is a powerful capability provided by the platform. Finally, we must discuss the policy evaluation logic that governs the entire IAM architecture. IBM Cloud follows a structured approach to policy enforcement, evaluating whether an action is explicitly allowed by a policy attached to the IAM entity or the resource itself. This evaluation follows the zero trust paradigm. Never trust, always verify. Every request made to the platform is scrutinized against these defined policies in real time, regardless of whether the request comes from an internal network or the public internet. This design ensures that unauthorized interactions are blocked by default, creating a robust security perimeter that scales with your infrastructure. By carefully architecting your policies to follow the principle of least privilege, you can fundamentally increase the safety and reliability of your cloud-native applications. See you in the next lecture. Welcome back. This chapter focuses on the mechanics of access control within IBM Cloud, specifically how we define exactly who can do what with our resources. In any distributed system, the principle of least privilege is the cornerstone of a secure architecture. By carefully mapping roles to specific users or service identifiers, we transform our security posture from a vague collection of permissions into a predictable, manageable framework. IBM Cloud utilizes identity and access management to enforce these policies, ensuring that actions taken against logical containers or individual resource instances are both intentional and compliant. When we talk about resource roles, we are essentially talking about the granularity of control we exert over the lifecycle of our cloud assets. Getting these definitions right is not just about security. It is about establishing a robust operational foundation that allows teams to work independently without risking the integrity of the broader environment. By understanding how to apply these roles to resource groups or specific service instances, you gain the clarity needed to scale your operations while keeping your attack surface strictly defined. Platform management roles serve as the administrative backbone for organizing and maintaining the environment at scale. The administrator role provides the most expansive scope, typically allowing for the full lifecycle management of resources, including provisioning, deletion, and the delegation of access to other users, which makes it a role to be assigned with extreme caution. Moving down the hierarchy, the editor role allows for operational modifications and resource management, but often excludes the ability to modify access policies themselves. The operator role acts as an intermediate tier, permitting the monitoring and maintenance of existing infrastructure without necessarily granting the power to perform destructive actions or major reconfigurations. Finally, the viewer role is the most restrictive platform role, designed strictly for auditing and observation, ensuring that personnel can gain insights into the current state of the platform without the capability to trigger any state changes. These roles are fundamental for maintaining a separation of duties, ensuring that your provisioning pipelines are as orderly as your production environments. While platform roles manage the lifecycle of the container or the environment, service access roles are designed to govern how we interact with the specific capabilities provided by individual cloud services. A manager role in this context typically implies administrative oversight of the service's internal configuration and data, while the writer role allows for active contributions such as uploading data, updating application configurations, or modifying resources managed by that specific service. The reader role, conversely, is scoped to permit the consumption of data or the inspection of service-level metrics without permitting any alteration of the underlying assets. These roles are essential because they prevent a user with broad platform access from inadvertently or maliciously modifying data within specific services where they might lack the domain expertise or authorization. By explicitly defining these interactions, we create a system where developers can function within their specific service boundaries effortlessly, confident that their actions are natively consistent with the broader security policy. These interactions are managed centrally, providing a consistent audit trail that reflects exactly who accessed which service, the nature of their activity, and the time frame of their interactions. We will continue our exploration of cloud security principles in the subsequent session. Welcome to our exploration of IBM Key Protect, a critical component in your cloud security architecture. In this chapter, we will master the intricacies of centralized key management within IBM Cloud to ensure your sensitive data remains protected. IBM Key Protect serves as a centralized, highly available service designed to manage the lifecycle of your encryption keys. At its core, the service leverages Hardware Security Module, or HSM technology, to meet FIPS 140 to 2 Level 3 security requirements, providing a robust root of trust for your cryptographic operations. When you entrust your keys to Key Protect, you are shifting the burden of secure storage, auditing, and management away from your application code and into a managed, hardware-backed environment. This separation of concerns is a fundamental principle of sound security design, as it limits the blast radius should an individual application component become compromised. By centralizing these operations, organizations can enforce uniform security policies across diverse workloads, ensuring that every deployment adheres to the same strict standards. Because the service is native to the IBM Cloud platform, it integrates seamlessly with other services like object storage or block storage, allowing for a frictionless transition to encrypted workflows. Key Protect does not merely store your keys. It acts as an intelligent orchestration layer that monitors and enforces compliance for every cryptographic interaction. This predictably secure environment allows your developers to focus on building features rather than wrestling with the complexities of managing physical security appliances. The lifecycle management of customer-managed encryption keys is perhaps the most significant functional advantage of Key Protect. When you move away from provider-managed keys, you take ownership of the generation and retirement phases of the key's existence. Key Protect facilitates this by providing automated rotation policies, which are essentially predefined schedules that generate new key versions without requiring you to manually re-encrypt your data store. This automation is crucial for maintaining compliance with industry regulations that often mandate periodic key rotation to limit the potential utility of a compromised key. Beyond rotation, the service allows for explicit revocation, where you can disable a key to immediately and completely block access to all data that depends on that specific key. This capability serves as an ultimate kill switch if a security breach occurs or if you need to perform an emergency decommissioning of a service. Once a key is scheduled for deletion, Key Protect imposes a mandatory waiting period, ensuring that you do not inadvertently lose access to your data permanently. Meticulous logging of every lifecycle event ensures that your security teams maintain perfect visibility into who performed a key action and when it occurred. Envelope encryption represents the methodological backbone of how Key Protect achieves scale and performance without sacrificing security. In this pattern, your data is encrypted using a data encryption key, or DEK, which is stored alongside the encrypted data itself. Crucially, that DEK is then encrypted or wrapped using a key encryption key, or KEK, which remains safely stored inside the Key Protect HSM. By offloading the burden of secret storage to the KEK, you ensure that the more sensitive master key never leaves the encrypted, tamper-resistant boundary of the HSM. When your application needs to access the data, it sends the wrapped DEK to Key Protect, which decrypts it, and sends the raw key back only if the application has the appropriate IAM permissions. This strategy allows for high-performance encryption operations where large volumes of data can be processed by local application logic while the master key material remains strictly protected. Because the KEK never leaves the hardware boundary, the risk of interception or accidental exposure is inherently minimized. This architectural pattern is widely recognized as the industry standard for cloud-native applications, providing a robust and dependable way to maintain control over your data while leveraging the elastic nature of cloud storage services. See you in our next session. Welcome back. In this lesson, we will focus on the fundamental concepts behind data protection through encryption protocols in the IBM Cloud ecosystem. When we discuss the security of cloud environments, we primarily categorize data in two states: data at rest and data in transit. Data at rest describes information persisted on physical or virtual storage media, including block volumes, file systems, object storage buckets, and database records. In these scenarios, Encryption acts as a last line of defense, ensuring that even if the underlying storage medium is physically compromised or accessed without authorization, the actual data remains illegible without the decryption keys. IBM Cloud ensures that these volumes and buckets are encrypted, providing a foundation where security is baked into the storage layer. Whether you are dealing with a standard database instance or a high-performance block storage volume for your virtual servers, the protocol remains consistent in its application of cryptographic algorithms. You should view data at rest not as a static state, but as a continuous requirement for protecting the integrity of your workloads against unauthorized access. Data in transit, conversely, necessitates a different approach, as information moves across external internet connections or internal private network backbones. Here, the focus shifts to ensuring that packets cannot be intercepted or manipulated during their journey between your clients and the cloud, or between disparate microservices. Protocols like transport layer security are the industry standard for this task, establishing encrypted tunnels that authenticate both endpoints and obfuscate the payload. Whether traffic is traversing a public VPC gateway or moving across a private MPLS connection like IBM Cloud Direct Link, the requirement for robust encryption remains absolute. Implementing these protocols correctly prevents man-in-the-middle attacks and ensures that the communication path remains confidential throughout the entire network transmission process. By relying on proven cryptographic standards, you provide a secure envelope for data moving across the distributed infrastructure that defines the modern cloud architecture. We must distinguish between default provider-managed encryption and advanced customer-managed key configurations, as this impacts both your control and your security posture. By default, IBM Cloud manages the lifecycle, rotation, and protection of the keys used to encrypt your resources, which is often sufficient for general compliance requirements. However, certain industry regulations may demand a higher level of oversight, requiring you to utilize a service like KeyProtect or HyperProtect crypto services to maintain ownership of your root keys. When you choose to manage your own keys, you accept the responsibility of ensuring those keys are available, properly backed up, and handled according to strict organizational security policies. This distinction is critical for architects because it shifts the trust model from the provider to the client, which is often a prerequisite for financial, healthcare, or government-grade workloads. Understanding when to use provider-managed keys versus your own keys is a mandatory skill for achieving true compliance without introducing unnecessary operational risks into your environment. See you in the next lecture. Welcome back. In this section, we move into the landscape of industry compliance standards and the regulatory frameworks that govern modern enterprise cloud operations. Compliance is not merely a bureaucratic checkbox that you tick to satisfy an auditor, but rather an architectural constraint that shapes how we design and deploy our cloud infrastructure. When we talk about global regulatory frameworks, we are essentially discussing the rules of engagement for handling sensitive data across various jurisdictions. IBM Cloud positions itself as a robust platform that implicitly understands these requirements by embedding compliance controls directly into the fabric of its service offerings. This means that when you are architecting a solution, you are not building on a blank slate, but on a foundation that attempts to meet international expectations for data integrity, residency, and privacy. The primary objective of these standards is to ensure that enterprise workloads remain secure even as they scale across geographically dispersed data centers. Without these predefined certifications, organizations would be forced to reinvent the wheel for every security audit, which is neither efficient nor fundamentally safe. By relying on platform-level certifications, companies can shift their focus from proving that the physical infrastructure is secure to focusing on the logical security of their own applications and data configurations. This division of responsibility is a core tenet of the shared responsibility model, which you must internalize to operate effectively in the cloud. If we look at specific privacy regulations, we encounter frameworks like the General Data Protection Regulation, or GDPR, which has fundamentally changed how global entities manage personally identifiable information. IBM Cloud supports these regulations through specific technical capabilities, such as data residency controls, which allow you to specify exactly where your data resides within a global geography. This level of control is critical because, in many regulated industries, moving data across sovereign borders is simply not an option. Beyond data residency, the platform provides transparency through third-party attestations and audits, covering standards such as SOC 1, SOC 2, and ISO 27011. These certificates prove that the underlying infrastructure is governed by rigorous processes that are tested periodically by independent entities to ensure that controls are operating as intended. When you choose a cloud provider, you are, by extension, inheriting their compliance status to some degree. Being able to demonstrate that your environment runs on such a compliant substrate makes the path to your own regulatory certification significantly smoother and more predictable. It removes the ambiguity that often plagues early-stage cloud migrations, where security teams are unsure about the baseline posture of the cloud provider. Another essential aspect of this landscape is the application of these standards to industry-specific requirements, such as HIPAA for healthcare or PCI DSS for payment card processing. These standards are not suggestions. They are rigorous requirements that demand specific types of encryption, access logging, and incident response protocols. IBM Cloud provides dedicated compliance programs that map these high-level regulatory requirements to specific implementation patterns within their cloud services. For instance, when dealing with financial services, you might leverage IBM Cloud for Financial Services, which is designed with a specific set of security controls tailored for the unique risk profile of banking and fintech. This approach goes beyond standard cloud utility by providing a pre-validated environment that significantly reduces the enterprise effort required for auditing. By intelligently leveraging these built-in compliance frameworks, organizations can achieve a state of continuous compliance rather than relying on point-in-time assessments. This is a massive shift in how we manage risk, because it allows for architectural changes to be validated against security policies in real time. Ultimately, the maturity of these compliance offerings determines how quickly a business can move from a development lifecycle into a highly regulated production state. See you in the next lesson. Hello, welcome back. In this session, we will explore the essential security best practices required to architect and maintain a robust defense-in-depth posture within an IBM Cloud environment. Building a secure cloud environment is rarely about a single configuration setting, but rather the deliberate orchestration of multiple overlapping layers of protection. When we talk about defense in depth, we are essentially acknowledging that every control, regardless of how well it is implemented, carries a non-zero probability of failure or misconfiguration. To mitigate this, we construct a series of perimeters that require an attacker to traverse multiple independent security hurdles to reach sensitive data or resources. This begins with the identity layer, which acts as the new perimeter in a world where network boundaries are becoming increasingly fluid and ephemeral. We must strictly adhere to the principle of least privilege, ensuring that users and service identities have only the precise permissions required to perform their discrete functions, no more and no less. Beyond identity, we must consider the network itself, where segmentation plays a vital role in localizing potential breaches and preventing lateral movement across our various environments. By isolating workloads into discrete subnets and enforcing strict ingress and egress rules via network security groups, we significantly reduce the attack surface available to unauthorized actors. Encryption is another non-negotiable pillar of this strategy, and it must be applied both at rest and in transit without exception. For data sitting in storage buckets or databases, relying on platform-managed keys is a good starting point, but transitioning to customer-managed keys via services like Key Protect offers the granularity and control required for rigorous compliance and data sovereignty. When data moves between services or across geographic boundaries, you must mandate the use of modern, secure TLS protocols, effectively rendering captured packets useless even if they leave the secure confines of your virtual private cloud. However, preventative controls are only half of the equation, as true security requires the ability to detect, analyze, and respond to anomalous behavior in real time. Continuous observability, leveraging tools that aggregate logs and telemetry across all cloud resources, ensures that we are not flying blind. If a security group is modified inconsistently or an identity is used from an unexpected location, our monitoring system should provide the immediate visibility needed to intervene before that anomaly escalates into a full-scale security incident. Automation serves as the glue that keeps these security practices consistent and scalable across large-scale deployments. Manual configuration is inherently error-prone, and in the cloud, even a minor human oversight can lead to an unintended data leak or exposure of administrative endpoints. By adopting infrastructure as code patterns, we standardize our deployment logic, allowing us to bake security best practices, such as encrypted volumes, hardened machine images, and restricted network paths, directly into the template definition. This approach ensures that every resource provisioned in our environment adheres to institutional security policies by default, rather than by request. Furthermore, regular architectural reviews and automated compliance scanning allow us to detect configuration drift early. When we treat our security posture as code, we gain the ability to version, test, and audit our defenses with the same rigor we apply to our application source code, ultimately resulting in a more predictable and resilient architecture overall. Finally, we must recognize that security is not a static endpoint, but a continuous life cycle of hardening and assessment. The landscape of threats evolves constantly, and our defensive strategy must likewise adapt to new vectors and vulnerabilities as they emerge. By fostering a culture where security is integrated into every stage of the development process, often referred to as shifting security left, we move away from treating protection as a blockaded gate at the end of the pipeline. Instead, we empower our teams to make informed, risk-aware decisions throughout the design and construction phases. This comprehensive approach, combining identity management, network segmentation, robust encryption, and continuous monitoring, provides the foundation upon which secure, reliable, and compliant cloud applications must be built to survive in a modern, threat-rich environment. Mastery of these patterns will not only help you successfully navigate certification requirements, but will also provide you with the technical vocabulary necessary to discuss risk and mitigation effectively in a professional production setting. I will see you in the next lecture. Welcome to our module on Watson Artificial Intelligence Services, where we will examine how IBM brings enterprise-grade cognitive computing to your cloud environment. By the end of this section, you will understand how to leverage these tools to build intelligent, data-driven applications. When we approach the topic of Watson Artificial Intelligence Services, we are essentially looking at a collection of pre-trained and customizable APIs that allow developers to infuse cognitive capabilities into their cloud-native applications. These services are not merely black boxes. They represent a sophisticated stack of natural language processing, visual recognition, and machine learning algorithms that operate on the vast infrastructure of the IBM Cloud. To build a robust system, one must understand that each service is designed to solve a distinct problem, whether it is deciphering customer sentiment from unstructured text or automating the classification of visual assets in a massive database. By integrating these services directly into your deployment environments, you move away from traditional, rigid programming and towards systems that learn and adapt over time. The fundamental value proposition here is the ability to deploy complex intelligence without needing to manage the underlying data science overhead, which, as many of you know, is traditionally the most resource-intensive part of the software development lifecycle. These services communicate through standard RESTful APIs, which ensures that they remain platform-agnostic and easily consumable within your existing microservices architecture. Ultimately, the effectiveness of these tools relies on how cleanly you feed them data and how predictably you configure their parameters to meet your specific enterprise requirements. Natural language processing stands as the core pillar of the Watson ecosystem, providing the engine for everything from simple chatbots to complex document analysis platforms. When we talk about natural language understanding, we refer to the ability of the system to extract entities, analyze syntax, and determine the intent behind a given string of text. Because these services are natively integrated into the IBM Cloud framework, they allow for rapid scaling as the volume of inputs increases, which is critical for businesses experiencing seasonal spikes in traffic or data ingestion. The maturity of these algorithms means you can rely on them to handle diverse language patterns with a degree of precision that would take years to replicate with custom-built models. Furthermore, the deployment process is designed for continuity, meaning that an application you build today will continue to function reliably even as the underlying service APIs receive security patches or back-end performance improvements. This reliability is the hallmark of the platform, as it shields the developer from the volatile nature of experimental artificial intelligence research. When auditing your own architecture, consider how these natural language services can serve as a conduit for automation, reducing the manual effort required in customer support workflows and data entry tasks. It is this intelligent automation that transforms a standard cloud presence into an environment capable of genuinely improving business outcomes through data visibility. Beyond linguistic comprehension, the Watson platform provides specialized capabilities that handle unstructured data in ways that maximize operational efficiency across the enterprise. For organizations dealing with large volumes of audio, video, or imagery, the machine learning models embedded in these services act as an automated force multiplier that processes information at speeds human teams simply cannot match. The integration process is deliberately seamless, designed to fit into standard CI/CD pipelines so that your updates to the artificial intelligence logic are as safe and predictable as your code changes. Security, of course, remains a paramount concern, and IBM has architected these services to satisfy strict compliance standards, ensuring that data is encrypted at rest and in transit as it flows through the cognitive analysis pipeline. When you choose to include these services in your cloud architecture, you are effectively offloading the complexity of maintaining sophisticated machine learning workloads to a managed provider. This allows your team to focus exclusively on the business logic rather than the low-level infrastructure requirements that usually trap organizations in technical debt. By systematically applying these tools, you are not just adding features to an application, you are creating a foundation for ongoing autonomous growth that aligns perfectly with modern enterprise requirements. See you in the next lecture. Welcome back. In this chapter, we will explore the Internet of Things, focusing on how distributed sensor networks function alongside edge computing and messaging protocols. The Internet of Things, or IoT, represents a paradigm shift where physical objects are equipped with sensors, software, and other technologies to exchange data with other devices and systems over the Internet. At its core, this is about transforming passive physical infrastructure into an active, data-generating participant within an ecosystem. When we talk about these systems on a platform like IBM Cloud, we are rarely discussing just a single device sending a signal. Instead, we are looking at distributed sensor networks that must scale to support potentially millions of remote endpoints simultaneously. The primary technical challenge here is not just connectivity, but the reliable ingestion and processing of telemetry data at a massive scale without compromising system performance or data integrity. Think of it as moving from static monitoring to dynamic, real-time awareness, where every sensor acts as a node in a much larger, cohesive fabric. To make this work, we rely on specialized messaging protocols designed for bandwidth-constrained environments, with MQTT being the most prominent example. When these millions of devices generate continuous streams of telemetry, sending everything directly to a central cloud data center becomes impractical due to latency and network congestion. This is where edge computing becomes essential, allowing us to perform data analytics and filtering closer to where the data is actually generated. By pushing the computational workload to the edge, we reduce the amount of raw data that needs to traverse the network while ensuring that critical insights are derived in near real time. This architectural pattern essentially distributes intelligence across the network, ensuring that the cloud core remains decoupled from the noise of low-level sensor input. We must securely register each device to ensure that only authorized entities can communicate with our backend services, which requires robust identity management at the device level. Because these devices often exist in physically insecure locations, we treat every connection as potentially hostile, necessitating encrypted communication channels by default. Ultimately, this approach creates a resilient pipeline that moves data from the edge to the cloud, allowing us to analyze, store, and act upon information with high precision and reliability. Managing these remote devices effectively requires a clear understanding of the lifecycle of an IoT asset, from provisioning and secure onboarding to decommissioning. We want systems that function cleanly and intelligently, without requiring manual intervention for every single minor configuration change or security patch. This is why we rely on centralized control planes that treat these devices as individual resources, similar to how we manage virtual machines or container clusters in more traditional cloud architectures. If we look at the communication layer, we focus on the efficiency of telemetry transport, ensuring that heartbeat signals and status updates do not consume excessive power or data. This is particularly important for battery-operated devices that need to operate in the field for months or years without maintenance. By designing our IoT systems with these constraints in mind, we build solutions that are not only robust against hardware failures, but also capable of scaling horizontally as the number of managed devices grows. This is the foundation of building a modern, data-driven environment where the physical and digital worlds converge seamlessly and securely. See you in the next lecture. Welcome to the chapter on blockchain on IBM Cloud, where we will examine enterprise-grade distributed ledger technologies and their practical application. This module is essential for understanding how to integrate immutable ledgers into your cloud architecture with total confidence and security. Blockchain is essentially a distributed ledger technology that ensures transparency and immutability across a network of participants by removing the need for a central authority. In an enterprise context, such as the solutions hosted on IBM Cloud, we are primarily dealing with permission ledgers rather than the public anonymous networks commonly associated with cryptocurrencies. This architecture allows organizations to trade assets or verify processes with the assurance that every transaction is cryptographically linked to the previous one. When you deploy these solutions, you rely on smart contracts, which are self-executing portions of code that automate agreements once specific conditions are verified. Because these contracts reside on the blockchain, they operate in a tamper-proof manner, providing a level of reliability that traditional centralized databases struggle to match. Maintaining this state requires robust consensus algorithms that ensure every node in the network agrees on the validity of transactions before they are committed. Through IBM Cloud's managed offerings, these complex components are handled to ensure the infrastructure remains available and secure without requiring you to manage the underlying physical hardware layers. At the heart of many enterprise blockchain solutions on the platform is the Hyperledger Fabric framework, which provides a modular architecture for building blockchain-based applications. Hyperledger Fabric is distinct because it introduces the concept of channels, which essentially allow for private subsets of a network to conduct transactions that remain invisible to the broader network. This is a critical feature for businesses that need to maintain regulatory compliance while still participating in a larger distributed ecosystem. Furthermore, identity verification is managed through a membership service provider, ensuring that every participant is explicitly recognized and authorized to interact with the ledger. By combining this granular control with high-performance cryptographic signing, you create a system where data provenance is never in question. When you deploy these environments, the system manages the complexity of certificate authority distribution and peer synchronization, allowing you to focus on the business logic rather than network maintenance. This seamless integration ensures that as your consensus demands grow, the platform scales efficiently while still upholding the integrity and immutability that define the technology. Implementing these technologies efficiently requires an understanding of how managed services in IBM Cloud abstract away the manual configuration of components like orderers, peers, and certificate authorities. You are essentially shifting the burden of operational consistency to the service provider, which monitors the health of the ledger constantly and automatically. This approach brings peace of mind, as the system intelligently manages resource allocation and load balancing across nodes to handle transaction throughput patterns. You get the benefit of a logically separated, secure environment where data is encrypted both at rest and in transit, fitting neatly into broader enterprise security frameworks. Because these managed services are designed for the enterprise, they support standard identity access management protocols, making it easier to integrate blockchain operations into your existing Active Directory or identity provider workflows. Ultimately, the maturity of these tools allows you to bridge the gap between abstract distributed ledger theory and effective production-grade business processes. See you in the next lecture. Welcome to this lesson on the IBM Cloud Pricing Calculator, where we will demystify how to translate architectural designs into concrete financial projections. By the end of this session, you will understand how to utilize this tool to move from abstract infrastructure requirements to validated budgetary constraints. In the domain of professional cloud architecture, the ability to predict costs with high precision is as critical as ensuring high availability or robust security. When you are tasked with designing a cloud solution, you are essentially balancing technical requirements against economic realities. The IBM Cloud Pricing Calculator serves as the primary utility for this purpose, allowing you to quantify the capital and operational expenditure associated with various cloud services. It is not merely a tool for providing a rough estimate, but a systematic framework that allows you to construct a granular bill of materials for your proposed architecture. By inputting specific usage patterns, instance types, and storage volumes, you generate a data-driven forecast that accounts for the diverse pricing models inherent in cloud computing. This enables you to present a transparent and defensible financial model to stakeholders, ensuring that your technical choices align seamlessly with the allocated project budget. Understanding the mechanics of this tool is a prerequisite for any architect who aims to deliver projects that are not only technically sound, but also financially sustainable and predictable over the long term. The calculator is structured to accommodate the modular nature of IBM Cloud services, reflecting the decoupling of service components. When you begin a project in the calculator, you start by selecting the specific services relevant to your architecture, such as virtual servers for VPC, object storage, or managed Kubernetes clusters. For each service, you are prompted to define variables that influence the cost, such as CPU cores, memory allocation, storage throughput, and data transfer rates. This, in essence, is an exercise in resource modeling. Instead of thinking about the service as a monolithic entity, you decompose it into the billable units that the platform tracks. For example, when you provision storage, you must consider the storage class, the requested capacity, and the egress frequency, as these are the levers that dictate the monthly cost. By systematically selecting these variables, you prevent the common pitfall of underestimating costs by ignoring ancillary expenses like inbound and outbound data traffic. This methodology empowers you to simulate different architectural variations, allowing you to compare the cost impact of choosing, for instance, a bare metal instance versus a virtual server in a VPC. Beyond simple service selection, the pricing tool provides essential features for managing multi-service deployments and scaling scenarios. One of the most powerful capabilities is the ability to export your estimates as a shared quote, which facilitates communication between technical teams and procurement departments. You should look at the calculator as a way to create a living document that evolves alongside your architecture as it progresses from a conceptual design to a production-ready environment. If your design requires high availability, you will necessarily be doubling or tripling your resource footprint across multiple zones, and the calculator allows you to reflect this scale immediately. Because cloud billing is often based on consumption, you must also be disciplined about specifying the duration of your usage, whether it is for a short-term proof of concept or a long-term enterprise deployment. Consistency is paramount here. Maintaining a standard approach when naming and organizing your estimates ensures that you can compare apples to apples when auditing your architectural decisions against the actual consumption patterns later in the development lifecycle. You must bear in mind that the accuracy of your estimate is strictly bounded by the fidelity of your architectural requirements. If you enter imprecise values into the calculator, you will inevitably receive an imprecise financial projection. Therefore, treat the tool as a feedback loop for your design process. If the resulting quote exceeds your budgetary constraints, it acts as a signal that you need to reevaluate your architectural trade-offs. Perhaps you can optimize storage tiers, move from high compute instances to more efficient alternatives, or leverage reserved instances to lower your unit costs. This iterative process of estimation and refinement is what defines an effective cloud advocate. You use the calculator to validate your assumptions and to ensure that the infrastructure you build is logically and financially sound. By mastering the tool, you gain the confidence to lead architectural discussions with a clear understanding of the fiscal implications of every technical decision you make. It is about closing the gap between the promise of cloud scalability and the reality of organizational budget management. See you in the next lecture. Hello, and welcome back. In this chapter, we explore how organizations align their technical consumption with financial strategies, specifically focusing on cloud subscription models. When we talk about cloud subscription models, we are really discussing the abstraction of financial commitment from physical asset procurement. In a traditional IT environment, the capital expenditure model dominates, requiring organizations to estimate capacity requirements years in advance and pay upfront. Cloud computing shifts this to an operating expenditure model, where financial consumption aligns more closely with actual service usage. IBM Cloud offers several variations of this, ranging from fully elastic consumption to structured commitments that provide cost predictability. Understanding these differences is not just an administrative task, but a core requirement for any cloud advocate, as it directly impacts how architectural decisions translate into organizational budgets. We need to distinguish between pay-as-you-go, subscription, and enterprise-level discounting architectures, because these choices fundamentally alter how efficiently a department operates. The foundation of modern cloud billing is the pay-as-you-go model, which provides the highest level of flexibility for experimentation and unpredictable workloads. In this arrangement, you are billed in arrears for the resources consumed per hour or per second, reflecting a truly elastic approach to infrastructure. This eliminates the need for long-term contract negotiations when starting a new project, allowing developers to provision services instantly without architectural friction. However, this flexibility often comes with a higher per-unit cost compared to committed models, as the cloud provider assumes the risk of idle capacity. For steady-state workloads, rely on pay-as-you-go for initial prototyping while keeping a close eye on your usage metrics. Once a workload demonstrates a predictable resource footprint, transitioning to a more structured subscription or commitment model often yields significant cost optimizations. Subscription commitments represent a collaborative financial contract where the user agrees to spend a certain amount over a fixed period in exchange for discounted rates. This approach, often referred to as a committed spend, allows enterprises to balance the need for elasticity with the requirement for predictable budget forecasting. By providing IBM with a forward-looking view of your planned consumption, you gain better price transparency and a more favorable economic framework for scaling your operations. These agreements are not merely about securing a lower unit cost. They serve as a strategic bridge between the technical team's need for cloud-native agility and the finance department's demand for cost control. Effective financial governance in the cloud relies on selecting the right subscription tier that matches your anticipated growth trajectory. When analyzing these options, always consider the projected duration of the application lifecycle and the potential for seasonal spikes in service demand. Beyond basic subscriptions, enterprise discounting architectures allow larger organizations to aggregate their total spend across multiple accounts or business units to reach higher discount thresholds. This model encourages central management of cloud resources, as scaling across the organization directly contributes to improved economies of scale for the entire enterprise. Promotional credits serve as another layer in this financial ecosystem, often used for migrating existing workloads or accelerating the adoption of new platform-specific services. These credits can act as a catalyst for innovation, lowering the barrier to entry for teams looking to experiment with advanced technologies like artificial intelligence or complex data analytics. It is vital to manage these credits systematically, ensuring that they are applied to the appropriate resources to maximize their utility. By combining enterprise-level discounting with intelligent credit allocation, organizations can create a sustainable, high-performance environment that remains fiscally responsible as it scales. See you in the next lecture. Welcome back. In this lesson, we will focus on the structured approach required for managing support cases within the IBM Cloud environment. When issues arise in a production cloud environment, the efficacy of the support process depends entirely on the clarity and precision of the information provided to the service team. IBM utilizes a tiered support model designed to bridge the gap between initial incident detection and final technical resolution. To initiate a support case, you must navigate to the IBM Cloud Console and generate a dedicated ticket through the Support Center. This process is not merely a request for help, but a formal communication channel where specific diagnostic data serves as the primary input for the support engineers. Providing comprehensive logs, error identifiers, and a clear description of the steps to reproduce the issue allows technical staff to bypass initial troubleshooting steps and move directly toward identifying the root cause. If you provide vague descriptions, the support team is compelled to spend valuable time requesting clarification, which naturally extends the time to resolution. Efficiency in cloud operations is therefore directly proportional to the quality of the technical documentation you supply at the moment of case creation. By standardizing your team's approach to reporting, you ensure that diagnostic information is captured accurately and shared securely across the support lifecycle. IBM categorizes technical support requests based on severity levels, which define the expected response time and the urgency with which technical resources are assigned to the problem. Severity 1 is reserved for critical business impact scenarios where a service is entirely unavailable or suffering from a catastrophic failure that halts operations. Conversely, lower severity classifications are used for general inquiries, minor performance degradation, or non-disruptive configuration questions. It is a common misconception that escalating every ticket to the highest severity level results in faster service, but in reality, this often complicates the triage process and misaligns resources. Understanding these classifications is vital because service level agreements are strictly tied to the severity level you select during the submission process. When you correctly map your issue to the appropriate severity, you enable the IBM support system to route your ticket to the correct technical tier immediately. This logical alignment ensures that the support organization can function predictably, meeting the performance benchmarks promised in your specific support plan. Always verify that your contact information is current and that the specific cloud resource identifiers are included, as this allows the support personnel to examine the infrastructure precisely where the anomaly was documented. Managing a support case effectively requires a systematic approach to ongoing communication and monitoring until the incident is fully resolved. Once a ticket is open, avoid the habit of creating duplicate cases for the same issue, as this creates fragmentation in the audit trail and disrupts the continuity of the diagnostic effort. Instead, utilize the existing case interface to provide supplementary debug logs or to respond to requests for further environment details. You must treat the support case as a professional document that captures a distinct slice of your architecture's history, which might include specific configurations or recent changes made to your security groups and access policies. Security remains a priority throughout this process, so ensure that you do not transmit sensitive credentials or private keys in the case management system. If the support case requires remote access to audit your environment, use the authorized mechanisms provided by the IBM Cloud platform, rather than exposing raw server access to third parties. By maintaining a clean, documentation-heavy, and secure communication flow, you position your organization to recover gracefully from platform irregularities. This level of diligence ensures that you extract the maximum value from your support agreement and maintain the high availability goals critical to your cloud-managed services. See you in the next lecture. Welcome to the final segment of our preparation journey, where we reflect on the path we have traversed together. We have reached the conclusion of this course, marking the end of our structured review of IBM Cloud principles. Building a functional understanding of cloud computing requires more than just memorizing definitions. Throughout our time, we examined the fundamental pillars of compute, networking, storage, and security, while contextualizing them within the IBM ecosystem. By breaking down complex architecture, such as how regions and availability zones interact, you have gained the ability to see the underlying logic of distributed systems. We moved beyond simple service descriptions to discuss the operational realities of choosing between bare metal, virtual servers, and containerized environments like Red Hat OpenShift. This depth provides the necessary context to navigate the exam scenarios, as you now understand not just what a service does, but why it exists in the provider's portfolio. The shift toward modern development patterns, supported by serverless options like Code Engine and the integration of artificial intelligence via Watson, represents the current state of cloud innovation. You have learned how to manage these resources using identity and access management controls, ensuring that your architectural designs adhere to security best practices. Understanding how to utilize pricing calculators and subscription models is equally vital, as cloud engineering is inextricably linked to cost governance. Even as you prepare for the certification exam, remember that these skills carry long-term value in practical, real-world deployment environments. Consistency in your methodology, whether you are configuring VPC subnets or managing encryption keys, will serve you well when you move from test preparation to active cloud management. As you transition from this preparatory phase to the actual examination, trust in the rigor of your study process. Certification serves as an external validation of the technical competencies you have cultivated. But the true measure of your progress is the confidence you now feel when approaching architectural problems. You have explored the nuances of object storage resiliency and the importance of compliance standards, layering this knowledge into a coherent internal model. By focusing on the core mechanisms, how access control lists function, how resource groups organize the environment, and how global presence informs failure domains, you are equipped to analyze any question effectively. Approach the exam questions as puzzles that you can logically disassemble based on the principles we have discussed here. See you in your next professional endeavor.